Hello. Hello. Good morning. Very good morning. Are you guys happy?
Yes.
I know this is the last day of the school. I'm really disappointed. I wanted to be here for, 2 or 3 more days at least. All right, so for our last day, I've got the pleasure to introduce you to someone I know how to pronounce, José Antonio Carrillo de la Plata, right? And he is one of those success stories from the University of Granada. He actually studied here, not 1 degree, but 2 at the same time. So he studied computer science and mathematics, and he graduated in 1992. At that time, it's not like now that you can do a proper double degree. He basically registered for both degrees at the same time. And then, according to Google Gemini, the way Gemini describes him is as the world mathematician. Why? Because after Granada, he stayed here for a little bit as an adjunct professor at some point. Then he decided to go to Texas. Then in Texas, he decided to come back to Spain, Barcelona. Then I believe you went back to Granada, and then Imperial College, and that wasn't good enough. And now he's a professor at the University of Oxford. In there, and recently, I believe in 2020, he won one of the most prestigious awards you can ever get in Europe, which is the ERC grant, but the advanced ones. We've seen here the starting, the consolidator, and this is so much bigger. This is the advanced grants. Everything he does, as far as I understood, is all about PDE. What are PDEs? You have it there, come on. I know it's not there. Well, he will tell you all about it, and he describes and explains everything in this were based on partial differential equations. So, looking forward to your talk. Thank you very much, Jose.
Thank you.
Off you go.
Thank you very much, Isaac, for the nice introduction. It's always a pleasure to talk in Granada. For me, it's always coming back home every time I come and give a talk at the university. So today the point was to make a bit of connection of things that I'm doing mainly in the last few years, a couple of years, 3 years. I got interested into this direction, which is connecting the world of some problems in machine learning to some from the viewpoint of interacting particle systems. So I'm going to give you an idea of the things I have done. I started in using these ideas for optimization and sampling like 10 years ago, not that recent, but I will come back to machine learning later on. So I describe first some works related to optimization. So just to give you an idea from the point of view I'm going to take, maybe this connects with some of you that have been working maybe in particle swarming optimization. Let me give you an idea of consensus, what I call consensus models. So in fact, this came from a completely different application, and that's the power sometimes of mathematical modeling, that some ideas that you use in some things, then they give you ideas of how to do other stuff in other situations. So swarming is in fact something that has been studied in mathematical biology for many years. It's devoted to trying to understand the aggregations of agents of similar size and similar body type moving in a coordinated way. And it's something that has been used to model fish schools, birds, microorganisms, many things. Okay, so just to give you an idea of the basic bricks of the model there, just that you understand some of the simulations I will show, they are based on defining different interacting regions between individuals. So you know very well from COVID times, you don't want to be too close to others for obvious reasons, so you have some kind of inner repulsion zone, but you are social, so you want to be with others, so you have some kind of attraction area, and sometimes you are always, for whatever reason, you want to mimic the behavior of the movement of other individuals around you. So that's what I call the alignment part. So this leads to different type of models that you can use in each of these regions. I'm going to give you just one example, just for you to understand the viewpoint here. And you know, since I moved to the UK, I have only one God, and it's Newton, and it has to be always in my slides. So according to Newton, you can write some kind of second-order equations if you assume that each of the individuals, you can describe them by their position and their velocity, okay? So what you can write is that the derivative of the position is the velocity, fine, for each of these particles. Then here you have for the velocity two terms. Here you have this term, okay, so no, it doesn't show up, it doesn't matter. The first term there with the alpha and the beta describes somehow a tendency of all the particles that they want to move with the same speed. Typically, they would like to move with the speed, the square root of alpha over beta due to that term. The modulus of the velocity being the square root of alpha over beta. While the last one, it models the attraction and repulsion between the particles. It's an interacting potential. It's what usually we call it. And it tells you either that you're going to have an attraction or a repulsion force if you are, depending on the distance. So if you are closer to me, maybe the force that you impose on me is a repulsive force. If you are far from me, it will be an attractive force. Okay, so this is essentially what I just said. Just to give you an example of the potential can be just a combination of exponential functions. And if you choose them in the right way, then they are exactly of the kind of force that I just explained you. And what is interesting about these models? Let me just run the simulation. It's a simulation, 200 particles in which the center of mass is at the center of the window. And you see that at the beginning looks like they are not doing any particular behavior, but at some point, for instance, here in this simulation, you see that all of them, they arrive to consensus in the velocity vector, okay? They are moving in the same direction, and just centering the mass, the window in the center of mass, so that's why you don't see it moving, but it will be a flock of all those particles just moving in one direction. And there can be other stuff going on in that simulation that you had there. It seems, again, that everything is a bit chaotic, no order there of anything. But at some point, you will see that they arrive to some kind of behavior. In that case, just for fun, they are running around certain location at the end. Okay, so they give rise to a different kind of pattern. Okay, this is just a paradigm to give you an idea of the kind of model I want to follow. So if I want to model something like this, so let me just give you, this slide is just to show you one particular example of this alignment model, which is similar to what I'm going to show you immediately for optimization. So in this model, what I am saying is that I assume that I know the velocity vector to anyone in the room, and I can measure that. That has to be a very intelligent animal, but let's assume that they are able to do that. And then what I'm telling you here is that they would like to go to the average velocity that they can feel around. So that's why I'm doing this sum j, aij, bj minus bi. But the weights in which I'm going to consider that they do the average, they depend on the distance. Okay? So this is a quite kind of popular model in alignment. It's called the Cooker-Smith model. And you will see that somehow this is one of the reasons, one of the motivations we started to work on this from this point of view for optimization. Okay, so in this room, I don't think I had to convince you that an important problem is that if you have a function from Rd to R, particularly if D is large, and you want to optimize, find the minimum of that function, that is an important problem that had been tried to resolve by many different ways, meta-heuristics, different type of algorithms. I'm just listing some of them, and it's not, of course, exhaustive, okay? So the question is how to find a good, another method for global optimization that you can use in many applications, for instance, in machine learning to optimize your loss function. But the point of view I want to take is something, let me just comment on one of them. Simulated annealing. I don't know if you know about that particular method. Simulated annealing, in reality, what you are doing is the function that you want to optimize. You consider that as a kind of the potential in which the particles are going to move. And then you always move in the direction of the gradient descent of that potential, which is the function that you want to optimize. But in order to explore the positions in the landscape where you are evaluating the function, then you add some noise. Okay? So that's what is called simulated annealing, and in fact is solving, to be more precise, a kind of a stochastic differential equation, which is what I wrote there. Okay, that kind of method, you can call it a variant of that would be the stochastic gradient descent method. A variant of this method, you can use it, you can use it for optimization. The problem is that typically, well, it uses the gradient of the function. So you are assuming that you can compute the gradient of the function or approximate it very well. And that sometimes is a problem because the function might be quite irregular, or in large dimensions approximating a gradient is just difficult. So that might be a problem. And second, it is known that it has problems with shallow local minima. Okay, this is just so the goal is then to have to find an algorithm for minimizing a function. Typically think about that function as a non-convex function, so it might be complicated. And just an example, I'm just writing like a loss function, a typical loss function that you have in machine learning, which where you use some data, some control data for evaluating some loss function, and you take an average over the control. So why not a gradient method? So as I said, the gradient is hard to calculate. The objective function might be not smooth. Okay, these are some of the reasons. And also, as I said, you have problems. You have flat local minima, not shallow, as I said before. So typically, you have a situation like that in which you have a flat local minimum but a global shallow minimum. That is a typical situation in which gradient descent method is going to have issues. Why? Because you're going to typically get stuck in the flat local minima and not finding the shallow global minima. So, just to try to convince you, I did here a small computation, which is just using the steady state of the corresponding partial differential equation, PDE, that corresponds to the probability density of finding the particles at a certain location. So that particular stochastic differential equation, there is a law, there is a PDE that gives you the law of the finding the particles at the probability of finding the particles at position x at time t. And it follows that particular PDE. We know for that particular PDE, we know the exact steady state. The exact steady state is that distribution, which is usually, we call it the Gibbs distribution, is e to the minus beta, the loss function, normalized. The z is just making it a probability density. And then it's proven that if the probability of converging towards x1 divided by the probability of convergence towards x2, if you do that kind of method, is related to the steady state. That's the steady state, the limit of the PDE as t goes to infinity, and is related to that p infinity, and it can be obtained with that formula. H2 and H1 are the Hessians, around the location x2 and x1 of the function f. And then it's known that in that case, that probability, in fact, it tells you that it's likely to converge more to x1 than to x2. So for a stochastic gradient descent. So this is a strong reason why you would like to do something else. Okay, so how to okay, just an example. I mean, this is a Cook example of that kind. So we do a loss function, which is just an average of evaluations. We take that function depending on the parameter xi hat, which is just a translation of the second term. It's a function that has, well, I mean, one example has that shape. So if you do just as a simple test in one dimension, how it goes the SGD with this function, I mean, it finds the global minimum, which is that bullet point with 18% of at least of success rate on the trials that we did. Okay? So that's one of the issues. It's very well known, that issue. So I'm going to propose something different. And this gives you a bit the perspective I'm taking that I will take later on for other things for optimization or sampling. So that one is pure optimization. So let me explain you what we propose, like in 2018. So we have, let's say, n agents which are moving on the space of the parameters. Think about X, the parameter space, where you had your function that you want to optimize, your preferred loss function. And then I'm just telling you what is going to be the movement. Let me separate the two pieces. The first piece is just telling you you're going to move towards the location because you have minus lambda capital X minus V. So this is a simple relaxation from the location towards certain preferred location, Vt. And how I compute Vt, I'm going to tell you in a sec. That's where the things enter. For Vt, I'm going to take the average, the discrete average, or discrete expectation of certain function that I call omega f, which is related to the function f. I will tell you in a second which function I'm using. It's very much related to the Gibbs distribution before. So this is just the particles are directing towards certain location and fix that they change in time, which is given by that average. And then the second part is very similar to the simulated annealing. I just add some noise. But the noise, I add it also depending on the distance towards this average. Instead of being simple constant noise, I have also a dependence on the distance to the average. So the idea is I don't want to use gradient information. I just need to evaluate the function f at locations. So think about that I have a million of artificial butterflies that I send in Sierra Nevada, and I want to find the maximum of Sierra Nevada, which we all know where it is. So then, in between them, they are exchanging their location, their height, and then there is a big brother that collects all the heights, compute that average V, and then tell them, move towards that in principle. Maybe it's over there. Okay? That's the idea of the first term. Plus some stochasticity to let them know that they should explore a bit around, because you'll never know. Okay, so what's the function that we are taking? The function that we are taking is exactly e to the minus beta f. So it's exactly the same as the steady state of the simulated annealing, which is of that form, e to the minus the function f, multiplied by a factor, which if you want is like, think about f as s squared. That would be like the Gaussian, okay? Beta is 1 over the parameter that you put in the Gaussian. So I'm taking e to the minus beta, the function I want to optimize, and then the average that we were taking, you substitute, is kind of, you send n to infinity, you send to the number of particles to infinity, is an approximation of that average. What is rho t there? Okay, so this is the first time that it appears. Rho t, for me, is going to be always, I think about, if I send n to infinity, the number of particles to infinity, I may have an evolution of a probability density of finding the particles at location x. So rho tx gives me the probability of finding the particle at location x. And sometimes it's easier to work with the object, rho tx, than with the particles themselves. Because if you are able to say something about the distribution of rho tx, then you may come back to the particles. That's the philosophy. And that's what is called a mean field PDE, that it was in the title of my talk. So in fact, I want to find the evolution of the rho tx, and I will show you probably in a sec some PDE that gives me the evolution of rho tx. But just in that line, I just wanted to tell you what I expect to be the average of, the limit of the average when the number of explorers goes to infinity. So I expect to be that kind of average. So you see it's normalizing the exponential by the exponential of minus beta f, normalizing with respect to the measure of that gives you the probability density of particles. So it's a kind of average. So in fact, you can write it as an average of that probability density. Okay? That's what I meant. You take e to the minus beta f, multiplied by rho t, the probability of finding particles at location x, and then you take the average, or the expectation, if you want, depending on how you want to call it, the expectation of that probability measure gives you exactly that number. And what's the intuition about using this function now? Well, this needs to know a little bit about probability theory. There is a principle that is called Laplace principle that is very well known for many years, and there are books and books about this, that tells you this, tells you that information. Let me just try to gather what is the information that you know. So if you take the integral of e to the minus beta f and you multiply and you integrate it against something, you take the log of that and you divide by 1 over beta. Of course, this is kind of a limit that is complicated to take, a limit beta going to infinity of that quantity, but the fact is that under certain assumptions on rho, this is known. What you get at the limit is precisely the minimum of the function, the minimum value of the function. Okay? So the limit of that quantity gives you the value at the minimum. So the intuition about choosing this function is that by choosing that quantity goes to the value of the minimum, your distribution will get closer and closer to be concentrated on the location of the minimum. Okay? And this is what it means, this relation here. What I want is that that measure gets concentrated, more and more concentrated, at a location, which in mathematical terms, it means that is a Dirac delta at the location x bar. Yesterday already in some talks, Dirac deltas appear, so this is just a probability measure that is probability 1 of being an x bar, 0 outside. So no, this is a deterministic probability measure. Okay, so that's the intuition. So very similar to the kind of Cooker-Smale interaction that I was showing before in the swarming model. Is very, very much in the same spirit. Let me show you how it works. So this is just, again, an academic simulation in 2D with some particular function which has lots of local minima and one global minimum that is in the center here. So the location of these red bars are the location of the explorers, and they were distributed. And then just with 10 of them, you see, by using those parameters, let me just run it again, then they are able to find the location of the minimum. Okay? Which is what you want. I think I have, yes, it was the same, another simulation, similar simulation with different parameters. Okay, so now let me explain you the point of view again that I want to take. I want to take the point of view I send the number of particles to infinity, the number of particles that I use to find the minimum. Why? Because then in that way I can probably write evolution of the probability density that I was referring to. And this is doable. This is doable. Let me forget about the first part, which is writing in terms of stochastic differential equations that might be a bit more complicated. What you have equivalently is an evolution for the probability density of particles at location x. So similarly to the one that I told you before of the simulated annealing, here what I get is that. Okay, so essentially you get a term which is the Laplacian of something with a complicated non-local function inside. The Laplacians are just second derivatives in principle. And then these terms is a divergence of that quantity. Okay, so for us, of course, this is completely a kind of mathematical tool to understand the system. Because we are not going to use the PDE to solve anything, because this is like saying if you are going to do it in machine learning applications, you have 300 variables, that would be a PDE in 300 variables, impossible to solve numerically. That's not the point. The point is that this is, in principle, the PDE that you will get when n goes to infinity. So if you study this, then maybe you get an information also about the system in terms of how performant is, because it's at the end the limit of the particle system. So that's the hope. Okay, in any case, again, an academic run. So if you do this in one dimension exactly for the function I showed you at the beginning, so that's the typical evolution of your probability density. Okay, the probability density now is a function of x, it's a continuous function in x. And you start distributed, and it gets concentrated at the location of the minimum. Okay, that's the idea. Great. So how to do that? I'm not gonna give you an idea of that, but at the end of the day, there are two steps essentially. First of all, that's why we call it consensus-based optimization. First of all, you prove that your solutions will concentrate somewhere. So meaning that as t goes to infinity, when t is large, they will concentrate around certain location. That's what it means this. And second, you prove by the Laplace principle that that location, choosing the beta large enough, is as close as you want to the minimum. There are these two steps. Okay? But nevertheless, we do have results of convergence for the PDE. Unfortunately, and then I want to mention there, we can even quantify how long does it take to get to the minimum. So you could say, okay, fantastic, you have solved the global optimization problem. But it's not all. You would like to have such a thing for the m particle approximation, okay? Because that's the one that is really practical. And for that, the people are still working, but we don't have a definite answer. So there are some results about the rate of convergence. We talk about the rate of convergence for the m particle system, how far or how close is from the rate of convergence that you have for the full PDE. Okay, so coming back to this idea, let me doing the exploration on cases in which you have a flat streamer and a shallow streamer. So there is one aspect, this is a bit more technical, but I want to explain that we really would like to have good estimates that we can do the optimization problem in large dimensions. Okay, so this particular method that I showed you, it has a problem. Okay, so it's not perfect for the following reason. So that would be the practical scheme. And let's see that the problem, in fact, is that that would need that lambda, the parameter there, has to be of the order of the dimension. Okay? And that would be really bad if you want to use it in practice. Okay? In a large dimensional problem. So it's bad for high dimensional problems. One can check that, and the easiest way to check that is to look at what is called the variance of the particular configuration of those particles. Okay? So there is an improvement, and this is a bit of a technical improvement. The technical improvement is not to do the noise. You see, the noise part depends on the distance. So you do the noise part instead of depending on the distance, depending on the difference towards the average, but component by component. So you do component-wise noise with the distance towards the minimum. That you change the part in which the particles explore, in a sense. So you do that, and if you do that, so the intuition would be that you explore better and you have more chances to find the global minimum with less conditions. So let's compare the previous model and the new model with this variant. Let's assume that we know where the location is and is just fixed, the x star. And then we take the simpler case of that stochastic differential equation, or PDE, depending how you want. So what I'm doing here is to compute the evolution of the variance. Okay? So I'm computing the evolution of the variance, and for the variance, you can compute finally, and that gives you the evolution of the variance. The variance is the expectation of x minus a squared, so the variance around the global minimum. And if you do the whole computation, then by fixing just the direction of towards the minimum, then you see that you have that exponent in front of the evolution of the variance, minus 2 lambda plus sigma squared d. That's the bad part, because lambda then will have to be larger than sigma squared d divided by 2 in such a way that you converge to the minimum. So it's bad because it depends badly on the dimension. So if you do the same algebra with the variance, but for the new way of exploring, which you do it component by component, you avoid, because you sum independently each dimension, you avoid the dimensional dependence, and you only need lambda larger than sigma squared. So you don't have that badly dependent dimension on the constraints. So what I mean is that there have been many people looking at different ways of improving those schemes based on those ideas. So the same idea as before. You can start with the particle system. You can go to the n going to infinity. You will get either a stochastic differential equation or a PD. And there you can prove things like what I said before, that the loss functional, you can control it as close as you want to the value of the minimum. That's what it means is, and you give an error term. Okay? So you can, for the continuum model and for the system, for the continuum model in the sense the limit that is going to infinity, you have a good theorem with, let's say, that gives you guarantees of convergence. So, yeah, this is just what it involves, the two terms in the error term. Okay, so coming back to this, to the academic example I showed you at the beginning. The academic example, you just repeat it now with this scheme. Well, you get 98% of success rate, same more or less conditions, okay? No use of the gradients. So it's, as usual in numerical methods, of course there are pluses and minuses, but in this particular case, well, it behaves much better than the stochastic gradient descent. Okay, so I hope that this example of optimization has given you a little bit the kind of point of view I'm taking always in some of these problems. These kind of ideas have been used for solving inverse problems, okay? And for not only for optimization, as I explained it to you, but also for sampling. So sampling is another of the kind of operations that one would like to do efficiently in large dimensions, related to some of the operations that you do in machine learning. So you have a distribution, a kind of potential given, and you want a good approximation of sampling of particles of e to the minus a potential. So let me now, I think that's, yeah. Let me now move to another presentation I have that I want to show you some more recent things. So it's like the second part in what I want to show you, these ideas. Okay, I need to stop this one first. And then show you this one. And then do that. Okay, so in this second part, I want to show you how to use, again, this kind of viewpoint in other two different problems. One of them is called the Stein variational gradient descent method, and the other one is about the transformers architecture for LLMs. Okay, so let me start with the Stein variational gradient descent. So what's the objective of that? Is to solve a sampling problem. So what is a sampling problem? The sampling problem can be stated very easily, but that, how typically one says, it's easy to say, difficult to solve. I give you a function v of x in Rd onto R. I take the distribution probability e to the minus b normalized. Z is the integral of e to the minus b. How to do a good efficient sample from sampling from rho infinity. So how do you produce particles that sample this distribution in an efficient manner. Okay? So what it means this, so for instance, just to give you again some graphical interpretation, if we are in 2 dimensions, I get v of x such that the contour lines of v of x are this kind of banana shape probability distribution. So I would like, if you do some kind of sampling in an easy way, again, you can do that by similar to the Fokker-Plan equation, similar to the simulated annealing. You can get that. That's what you get. But probably you can see it's not too nice from also even looking at it. It doesn't look like a super nice idea of using this sampling. But yes, by the way, sampling in 1 dimension is very well known how to do. But I wanted just to mention that it's extremely difficult for D large, because the main problem is that the normalization constant Z is computationally intractable. Okay, so that's what the statisticians will tell you immediately. So, so that's why the problem is complicated. What I show you in this sampling figure, it was to use this kind of equation. This is again the same equation as I showed you in simulated annealing, just with different notation. V is the F that I was using before. And that linear Fokker-Plan equation then is known how that it converges to this distribution, e to the minus b, normalized, the rho infinity, as t goes to infinity, and is known how to do it in which sense. This is in the sense of the Kullback-Leibler divergence. So the Kullback-Leibler divergence of the solution of that PDE converges to zero, in the sense that the Kullback-Leibler, relative Kullback-Leibler divergence towards rho infinity converges to zero. Okay, to be precise. Well, the Kullback-Leibler divergence, I guess many of you have used it in, at least for discrete cases. Okay, so it's just defined there. It's that way of measuring the distance. So, what is the Stein variational gradient descent? So I would start from here, and then I go up. In fact, the state variational gradient descent was proposed by a couple of authors, Liu and Wang, which are computer scientists in Austin, in Texas, in 2017, not long ago. And what they propose is, why not to use a kernel, K, in order to delocalize the functions, and then use a particle system of that kind. Okay, this is exactly copied from their paper. So this kernel K is a variable of x and y. Think about a kernel like in the sense of the talks that we were listening yesterday, but it has nothing to do with the reproducing kernels. And given that kind of kernel, they propose that scheme, okay? If you see it like this, well, the epsilon n's are supposed to be parameters that you use that are going to converge to 0 and that they can change from iteration to iteration. But in the easiest possible way, let's use them, all of them equal, okay? Then you recognize that this could be considered as a kind of delta t, okay? Because if you divide by that, you will have xn plus 1 minus xn divided by epsilon. It's kind of approximation of the time derivative of something. So in fact, the thing is that you can then write, again, a kind of differential equation associated to that, which will give you dxi dt equals this sum. And here you have a sum j. So you have the effect of all the other particles through the kernel K. So this is very much, again, in the same spirit of what I did before for the consensus-based optimization, which I have a term that depends on the location of all the others, or in the swarming model that depends on the position and velocity of all the others, okay? Because you have this delocalization due to the kernel K. So, and in fact, if you write, again, one can write, believe me on that, formally, you can write a PDE associated to that interacting particle system in many occasions. This goes very much in the spirit of something that it was explained in passing yesterday in one of the talks. You take what is called the empirical measure associated to the ODE, which is a sum of Diracks at the location of the particles, and then you can check that the empirical measure is a solution of certain PDE in some sense. And believe me, the PDE that you get is the one on top. So again, you have a time derivative of the probability density of finding particles at location x, and you have that kind of term, divergence, rho, and integral, and then you have this integral with the kernel, kx comma y, of that quantity. If you look at this, this is that equation, and that's why I was talking about the localization. That equation is a local equation in the sense that it depends only on values of x at location x. Here, when you do that with the kernel x, kx, y, then that integral here delocalizes and uses all the other values of the same quantity. This is, again, the quantity gradient rho plus rho gradient v. So, okay, so one of the things that we have done in this respect is to look at what can we say about the rate of convergence towards sampling in time of that PDE. Can we say something like that? Can we say that it converges and it converges fast, or if it converges faster than the other approach? Can we get some advantage of that method? So let me get the story short. This is where, again, functional analysis enters, and there is a lot of behind, which I'm not going to show you, which is related to the Fourier transform of things, like very much in the spirit of some of the talks yesterday. But you can get an inequality that will tell you a relation between the Kullback-Leibler divergence towards the sampling distribution, rho infinity, in terms of a quantity that I'm denoting by d squared, which is written there. It doesn't really matter that you understand the precise meaning of that quantity. It's just that quantity, okay? But the important thing is that this inequality can be used in conjunction with the first identity. And the first identity was known even at the discrete level by some people already, that the solutions of the PDE satisfy that identity. And then immediately you are able to prove that inequality, you prove that your Kullback-Leibler divergence not only converges, but it converges exponentially fast. And you can give a control on lambda. So our contribution here has been to find kernels K such that this is true. Okay? Because before in the literature, this kind of inequality was assumed to see what could be the answer, but most of the kernels that people had used in practice, they were Gaussian kernels. Gaussian kernels, they don't satisfy that. They have to be a bit more complicated to satisfy that, the kernels. But the kernels have to be singular at the x equals y to satisfy the inequality, but we can enter into that if needed. Anyhow, what our contribution here, it has been that we give conditions on K such that we had that exponential convergence. So just, some computational samples again for academic purposes in 2D. So you can have that kind of very nice now sampling algorithms for some of these distributions, in particular the banana distribution I showed you at the beginning. Okay? So, yeah, this, I'm going to skip this. I want to get into, yes, sorry. Yes, the only thing I want to say is this point. As I told you before, we can find kernels such that the inequality is true, and then we can say the exponential convergence, and we give a constructive way of finding the kernel. This is just an example, okay? We can find, in general, we have a family of kernels that we can find. This is just to give you an example. We can give the Fourier transform of the kernel, which is equivalent by FFT to give you the kernel if you want. And it's a way of finding the kernel in an efficient way. So I can give you kernels that we know that the convergence is exponential. Okay. So let me just finish my talk in 5 minutes, more or less, by giving you the idea of how to use this. This is quite recent. This is something we sent the paper for publication a year ago, more or less, and it's going on now. How to use this kind of approach for the transformers architecture. Okay, the idea is sort of similar. Here in this slide, I just try to summarize quickly the standard transformers without doing any particular variant. So you have the standard Q, key, and value matrices, okay, which are written there, Q, K, V. And just for notation, I'm denoting A, K transpose Q. Then you give yourself any vectors, which are your tokens, x1, xn in Rd, which are vector of tokens. Then you map the sequence x1, xn of vectors in Rdn to the next iteration by taking them through this function, okay? So what I mean is that you define this function, f of x1, xn, which is given by that operation, the matrix B multiplied by sum j, 1 to m, pij, xj, being each of the columns of, rows of pij that I denote by pi, computed by the softmax with that scalar product, okay? So I think that notation is more or less the standard notation. Okay, so what you do is you can write the transformers as a continuous evolution, the d, or you can write it again as a discrete, like x1 xn plus 1 equals xn plus delta t f, okay? But you can write also dxi dt. You can consider at the time continuous, the time, the interpolation for the evolution of the transformers, we call it time. And then you have dxi dt equals to the corresponding component of that function f in Rdn. Okay? So this is, by the way, softmax single head self-attention. I haven't mentioned that. The simplest possible case. Well, the thing is that, again, one can write a kind of PDE viewpoint by looking not at the particular tokens xi, but the probability density of choosing one token x. And that's what I call mu. Mu is a probability density. And then if your tokens are sampled from mu, then the expectation of that quantity is exactly the continuous version of that sum. Okay? So that discrete sum, as you take n to infinity in a sense, or you write it as an expectation, it becomes those continuous integrals. Okay? Integral of vy e to the qx dot ky integrating against the mu. And then one can see also that the corresponding PDE is something very similar to what I had before. I'm just denoting it differently here. Mu is the probability density, so you have time derivative of the probability density plus divergence of mu times the vector field, which is this quantity. Okay? So again, the perspective is, if we are able to say something about that PDE, that is a PDE in very high dimension, okay? But if we're able to say something about that PDE, maybe, again, we can get some conclusion about the particle system that would be the transformer architecture. So this is the viewpoint that we are taking here, and let me just give you small information that one can get there, that you are not able to do it directly on particles, on the transformer, discrete transformer architecture that normally you use. So, for instance, you can look at what happens if the initial data is a probability density that is a Gaussian with certain measure, with certain mean, and denoting by alpha naught, and certain covariance metrics, sigma naught. So this would corresponds to say our tokens at the beginning are in that Gaussian, okay, are drawn from that Gaussian. So what happens with the evolution of that Gaussian along the PDE? Then you can write an exact, in fact, in this particular case, it's exact. You can really show that the solution is still a Gaussian, and the parameters for the mean and the variance are given by the solution of those ODs for the mean and the variance. So you can write a explicit formula, even. Why this is interesting? Because this tells you then what happens when t goes to infinity again. You would like to know, are you going to have clustering or not? Which is the typical behavior that you want to see in transformers. Are you going to have a dimensional reduction that will give you the different answers by using transformer to the next steps? So do you have a dimensional reduction? So that's just to give you an example. I don't want you to read it, but yes, you can give information like that. Depending, let me just say that, depending on certain quantity that depends on all the matrices, this B, A is K transpose Q. So depending on the relation on the matrices, you can really say what is going on if the Gaussian is going to be concentrated in a lower dimensional subset, because you look at the eigenvalues and then you look at the eigenvalues that become 0, and then this gives you the directions in which it's going to degenerate, or if not, maybe the transformer here and not normalizing in this one, so then it may happen that they just diverge. Okay, so this was again meant as an example to tell you that this point of view might have some advantages to tell you information about the system, the particle system, by embedding it in a larger problem for a PDE where you have tools, or mathematical tools, that allow you to answer those kind of questions, and then you can come back. So that's the point of view of interacting particle systems. And I hope that you enjoyed the talk, and thank you very much for your attention.
Abreu,
I have some questions. One of the, well, first of all, congratulations for the very nice talk and the very nice presentation. So graphics are amazing. I have two questions. One of them concerning the first part, and this is what is the interest of this measure in your approach, because you mentioned this measure. So why this measure and no other measure? What is the particular interest of this? And the second question is, in the last part of the talk, you have talking about kernel, the role of the kernel, and then you said that the kernel were defined by positive, that they were positive definite kernel, right? And then the theorem of Aaron Sahin from the 50s said that every kernel like this is associated uniquely with a reproducing kernel Hilbert space. So I think that reproducing kernel Hilbert space are there, and I would like to be clear in this point, because then I am wondering about the role of such a space in your approach. And the last question at the end, in the very last result, when you talk about transformers, the result are in terms of eigenvalues or whatever. So this result is of time from technique of differential partial equation or from technique of spectral theory. How the proof of that result is related to what approach?
Okay.
So many questions.
Okay.
Sorry.
Yes, that's
Sorry,
fine.
sorry.
Let me go one by one. The first question about the GIS measure. I mean, the answer is this. In a sense, this is a GIS measure. Given a potential V, e to the minus V normalized is what is typically called the GIS measure associated to V. And there, typically, you want to do the sampling problem. That's the question. The role of the GIS measure in the first part of the talk, it was precisely to, because we wanted to optimize the function f, we wanted to have a distribution precisely such that we know that when some parameter goes to zero, the beta parameter, in fact, was going, yes, to zero, no, was going to infinity, the beta parameter in that case was going to infinity, then we knew that the GIS measure is getting more and more concentrated at the location of the minima. And that's why I was using that. I mean, I could use any other distribution that has that property, but the GIS measure is the standard one that people use for that. So that's the first question. The second question was, the last one I remember?
The positive kernel.
Okay, I thought it was the third question. Okay, so the thing is, yes, the K that we use here is a positive definite kernel. The issue is that is done in a different, enters in a different way. You are delocalizing that quantity, gradient rho y plus rho y gradient vy, and then the quantities that we want to control are quantities, it's the Kullback-Leibler divergence, because, which is this quantity, which involves the log. So it has nothing to do with the L2 norms in principle. So we didn't use anything from the reproducing kernel, kernel Hilbert spaces. Because we wanted to look at an inequality of that form, which generalizes inequalities that are used for the standard Fokker-Plan equations, which, as you see, the dissipation looks like a kind of non-local L2 norm, but not the Kullback-Leibler divergence. So, of course, we use a lot of techniques by doing in Fourier, which resemble a bit what you had to do for reproducing Hilbert spaces, but we don't use the theory at all there. So I don't this is not saying that it cannot be used and see if there is I mean, some of the estimates in the producing kernel Hilbert spaces can be used here. I'm not claiming that, but we didn't see how to use it. Okay, so we had to do this work on our own. So the question is, as I said, the contribution here was to find kernels such that the inequality is true. So because the question is vice versa, because I want the kernel such that I have the exponential convergence, because this will imply that my numerical method to do the sampling will converge fast. So it was kind of inverse question. Which kernel satisfies the inequality? Okay? And what was the third question?
The last one, the last result, concerning eigenvalues and so with transformers.
Yes, I mean, the thing is, you use the PDE to get close equations for the evolution of the mean and the variance of the Gaussians. Then it's a matter of studying the directions in which these Gaussians become degenerate, which has to do with eigenvalues of the matrices involved in the evolution. So yes, at the end you need to just understand the spectrum of those matrices, but then the PDE enters in giving you the law about how the Gaussians evolve. And these, if you want to guess it, starting from the transformer architecture, you don't see it, because there is not true that if I get discrete number of tokens and I have this Gaussian distribution of this discrete number of tokens, it will remain Gaussian. It's only in the limit that is true, when you have the expectation.
It looks like a type of the Ron-Frobenius theorem, something of this flavor.
You want, once you restrict to the Gaussians, yes. When you restrict to the Gaussians and you know the ODs for the Gaussians, yes. So the advantage of that is that it gives you, again, an intuition, which is not a guarantee, because I don't have a theorem for the discrete architecture, of telling you conditions on the matrices that will lead typically to concentrations in lower dimensional sets. That is what you want, as far as I understood, in practice. And this you have to correct me, because there are more people here that know about transformers than me.
Thank you very much.
On the first part, the consensus of the model for optimization, do you have experiments for some complex problem?
Yes.
To know really two questions: the scalability of the model, the size, because it is very important. There are some specific models with a perfect mathematical approach that they have good behavior when the dimension is not so high, less than 50 approximately. It's very important. In fact, the most, probably the best model in the literature based on matrix covariance is the best with dimension less than 10. And how is the behavior in your experiment in comparison with it? Because now there are more than 500 proposals, but without any mathematical justification, you know, and this is a problem.
Yeah, that's why precisely we wanted to give one that we thought that it will have a mathematical guarantee in that sense, in the sense I explained. Yes, what we did is with the second variant, when the parameters, they don't depend on the dimension, and precisely that's why I introduced that part. That one, we had used it for MNIST, for instance, which is 7,200 variables. The algorithm has to be adjusted. It has to incorporate some other randomness parts. I didn't enter into that, how to make it efficient, but it works quite nicely and competitive to other references like stochastic gradient descent. So that's as far as I can say. But I have to say we haven't done a super rigorous analysis of scalability from the practical point of view. There are other people that is not work I have done, in which they have looked at up to dimensions 100, and it seems it's working nicely, but a serious comparison with others, I don't think it has been done. It would be very interesting to do. In fact, I'm not following much more on that direction, but there is a GitHub group on consensus-based optimization that you can find all the where you can find all the information of all the variants that people have been using. It's called CVX, I believe, or something like this.
Do you have the software available, the code?
Yeah, the GitHub. This is what I'm saying. Yes, it's not mine. These people that have colleagues that have worked on that after, based on my work and others' works. Yes.
I would like to do this. I was checking the paper, but you have several papers on consensus.
Yes.
Yes. Later we'll discuss.
I can find the GitHub and send it to you.
Okay.
I mean, I don't use it directly now.
Okay, perfect.
But I can find it. I mean, this has been built by many other people that got involved into this. So I'm not developing that. It was initiated by one of my PhD students, and then now he is faculty in TU Eindhoven, and he is one of the main contributors to that CVX GitHub.
Okay, thank you.
Yeah, no problem.
Any other question in the room? Well, otherwise, we're going to give you a massive clap again. And then we go to coffee. Thank you. 30 minutes. Coffee break. How we doing? We good? So for our second talk, we are heading back to Portugal. Second Portuguese member of this winter school. After John, we've got Professor Pedro Henriques Abreu. I tried. I don't know how to pronounce it exactly, but that's the best I could do. He's an associate professor at the University of Coimbra with a habilitation. What that means is basically that he's got something even higher than a PhD. That's what I understand about what a habilitation really is. He's a prolific mentor. He has guided 64 master dissertations to completion. Do you sleep or you supervise during the night? I don't know how you do it. But his research is mostly focused on a data-centric AI approach. And that's what he's going to be talking about today. Apparently, he likes to amend the data to make data better for us to work and to deal with missing values and all those things we normally try to say they are not in our data, right? So that's what we all do. Henrique, Pedro, thank you very much for joining us. The floor is yours for the next 3 hours, right?
Four.
Four.
So, good morning, everyone. My name is Pedro Henriques Abreu. I'm a professor at the University of Coimbra. Let me tell you that the University of Coimbra is the oldest one in Portugal, dated from the 13th century. So if you've never been in Coimbra, you must go there during your PhD. I think it will have some magic. So first and foremost, I would like to thank you for the invitation to be here. Isaac and Paco, thank you for the invitation. And let me tell you, Isaac, that you really, really trust me. Why? Because you put my talk in the last day of the winter school after the talk of an Oxford professor. So it means a lot to me, So to the audience, let me regret, I think you will be disappointed with my presentation. Why? Because I will not talk about LLMs, finally. I'm sorry. I will talk about data quality and why data quality is so important in our times. So to illustrate the concept, I will use 2 case studies. The first case study is related to imbalance and overlap. And in the second case study, I will talk about missing values. I think at this point you have all the documents, right? So probably you will have the presentation and the Jupyter notebook that I will use, right? Well, if not, send me an email at the end and I will be glad to send. Okay? So the tutorial, the title of my tutorial of today is Understanding Data Difficulty Problems in Data-Centric AI Era. So let's start. So in 2017, The Economist published a discovery saying that data is the new oil. As you can see in this cover, you will see the most important technological companies in the cover. So at the time, you see Google, Facebook, Amazon, and others. But the problem we discovered is that The Economist did not mention that, like the oil, data has some impurities. To some research perspective, we are living now in the era of the Industry 5.0, which means that terms like human-centric, LLMs, and big data belongs to our daily lives. And how we can generate data? Well, we have multiple options. We have, of course, LLMs. We can use social media to generate our data. So at this point, you can think that we are living in the perfect world, right? And of course, if you are from my generation, we also have some free datasets repositories that contain a huge set of datasets that you can use in your research. But the problem is quantity is different from quality. And so, some authors claimed that getting information off the internet and also from LLMs is like taking a drink from a fire hydrant, which means that it is a very complex process. Also, if we're following a claim produced by one of the winners of the Nobel Prize of the Chemistry 2024, he claims at the time that a data bottleneck is holding AI science back. AI's usefulness for scientific discovery will be stunted without high quality data. So let's try to see 2 examples of it. So my first example is this site. The URL is this one, so labelerrors.com. In that site, you will see a lot of data sets that are used in many, many research works. So the idea of the site is to illustrate a little bit the noise that some data sets present in the labels. Okay? So only two examples to exemplify. So imagine these images. So probably it could be an apple, and some data sets say that it will be a t-shirt, and this one is more tricky one. So as you can see, it's a kind of a cat face, and some sites says it is an octopus. What is the problem? The problem is you will train your models with this kind of data, and at the end you cannot use your model for nothing. Another example. So as you know, today we have some journalists that has formation in AI. We see all the time this kind of thing. So this is a very simple situation to explain. So it is a car accident between two cars, but the question here is that one of the cars is an autonomous vehicle and another car is driven by a human. Okay? So there is a car accident, and the journalists say when algorithms mess up, the nearest human gets the blame. So the journalist assumes, first of all, that the algorithm has the capability to mess up, which is not correct. And probably, if we want to improve this title, probably we can say when algorithm is trained by erroneous data, these situations can occur. Okay? In the same move, we have Andrew NG. I think you already know him. But basically, NG points that the problem with using low quality data is that you can train your model, but at the end you cannot pass to the production phase. So it means that you are wasting your time, basically. So what is our goal here? Is to pass to imperfect data to what we call smart data. And how we can do it? Well, we need to use a data-centric AI approach. What it means data-centric AI approach, and what are the main differences between this approach and the model one. So it's very easy to understand. So in the model-centric AI, given a data set, you want to produce the best model. How you can do it? Well, typically you choose the best technique, and after that you are modify the loss function and try to vary your hyperparameters, right? So at the end you try to find out the best model for your specific data. In a data-centric AI approach, given any model, you want to improve the quality of your training data set. This is the main focus. Let's try to see in a more illustrative way. So you have two approaches, the model one and the data one, and in each of those approaches you have code and data. For the model-centric perspective, you are working on the code, and for the data-centric perspective, you are working on the data. And this is the main difference between them. So to conclude this subject, we have this stripe. So you might assume that we realize that our data is flowed. So you have three directions. Well, basically you only have one, but okay, let's try to illustrate three directions. So you assume that your data is flawed, which means that one possibility, and this is the one available, so you use data-centric AI to fix your data. The other two are completely wrong, but basically the first one say that, okay, you are living with data is flawed, so you delete all the data and starting over. So it means that you are in the infinite cycle, right? And the last one, the worst one, is that you already know that your data has no quality, but still you train your model and use it for anything, okay? So I think you know these Gartner graphics, okay? So the main goal of the Gartner is try to predict what will be the concepts of AI that will be present in our daily lives in a 10 years approach, okay? So as you can see, data-centric AI appears here as one of the concepts that we will lead for 5 years from now. So now we understand that, first of all, data quality means we just understand that data-centric AI will be the approach that we must follow. And if we think about the data mining pipeline, of course, depending on the authors, we can have 4 steps or 6 steps. But imagine that in your pipeline, you have 5 steps. The question here is that what will be the step that we analyze the quality of our data and we improve it? So it will be in the pre-processing phase. Okay? In the pre-processing phase, we analyze what will be the problems that our data contain, and then try to solve it. So in this particular step, could have imbalanced data and missing data. So let's jump for the first case study, imbalanced data. So as you can see, we have multiple definitions for imbalance as well as for the missing one. But when we have imbalanced data, typically occurs when the number of examples of one class is underrepresented in comparison to the other classes. Imagine this scenario. Imagine that we are working on a binary context. We have two classes, right? So the one that we typically say the majority one and the minority one. The majority one means that it is the class that we have more instances. And the minority is the class that we have less instances, and we need to understand how can we improve the instance of the minority class. In terms of quantification, we have several metrics that we can use. Typically, we use the imbalance ratio, which is the proportion between the number of instances of the majority class through the number of instances of the minority one. And why imbalance is so important to address? Well, typically, the standard classifiers assume that there is a balance between the class distributions. And as you will see later on, it will not be the best approach. So we already understand the problem and how we can address it. Well, we have typically two approaches, the data level approach, which is the most popular one and the one that I will talk about. And you have also the algorithm level approach. So in the data level approach, why these approaches are popular? Well, basically on 3 points. They have proven to be efficient, they are simple to implement, and most important in my perspective, they are classifier independent. Okay? So we have two approaches, the undersampling and the oversampling. Typically we use the oversampling. But the undersampling means that you will decrease, using a certain criteria, the instance of your majority class, and the oversampling means that you will increase, of course synthetically increase, the instance of your minority class. And what are the algorithms that are present in the literature that you can use? Well, the most popular one is SMOTE. Okay? How it means SMOTE acronym. So SMOTE means synthetic minority oversampling technique. And how it works? Well, it's very simple to understand. So this is an example of a binary class, okay? Binary context. So we have two classes here. The class represented by the green dot, and the class which is the majority one, and the minority class which is represented by the blue dot. Okay? So our goal is to increase the number of instances of the minority one. Okay? So how can we do it? First of all, we need to decide what will be the number of neighborhoods that we will use. After that, we choose 3, here 1, 2, 3, and basically we draw that line that try to guarantee that the new point that we will generate, represented here by the yellow dot, will be the point that belongs to the same class that we want, so the minority one. So the formula is more or less like this. So you choose a point that already exists, then you have the difference, and this alpha. This alpha means that you are trying to add some variance in the new point that you are creating. And like I said to you, the goal is try to have a new point that somehow in the same area as the point that already exists in our data set. As you can imagine, throughout the years, we have a lot of SMOTE variations. This is all very, very small part of it. So imagine this, imagine that we have our original data. Once again, let's continue working on the binary context. You have two kinds of points. The first point, the black ones, are the majority class. The red ones are the minority ones. So SMOTE works like this. I think you already understand. You have, for instance, safe level SMOTE and borderline SMOTE. What are the differences? As you can see, the borderline tries to create synthetic points in the border of the area of the minority class, and the safe inside in order to guarantee that all the points belong to the class. And finally, this is a bad example, but I need to show you ROS. ROS means random oversampling, and basically the method don't create new points. They only replicate the point that already exists. As you can see, the new points, the blue ones, are overlapped with the red one. So only the duplication of it. So it's not a good method, of course. So now we reach for our first work. At the end, I can send you all the papers, etc., etc., etc. So the first work has this title, Cross-Validation for Imbalanced Datasets, Avoiding Over-Optimism and Overfitting Approach. And this is a funny work. Why? Because I don't remember quite well the work that we already performed at that time. But basically, I really remember that one of my PhD students said to me, "Professor, I detect a setup error in some articles." And what is the error? Basically, the authors want to lead with oversampling and cross-validation. And the error was the authors are trying to oversample the entire data set and then after that use the cross-validation. What it means that in the training set and in the test set you will have all the same instances. Okay? So at the end you obtain over-optimism results. So what we did at the time was try to do a paper illustrate this error. Okay? So in this paper, we want to illustrate this concept. The over-optimism is when you run cross-validation after the oversampling, and of course we try to correlate it with the overfitting, which, as you know, is the capability of the generalization of your model. So in this work, like I said, you will have two approaches. The first one is the wrong one, okay, that performs oversampling before the cross-validation. And the approach 2 is the correct one. So it means that you run the cross-validation, you divide in train and test, and only in the training you perform the oversampling. Okay? This is the right way to do it. Of course, we try to characterize the over-optimism and overfitting in this kind of approaches. And after that, we try to somehow add the complexity metrics that I will talk about later on. And we try to understand what will be the best oversampling technique to use. So this is our experimental setup of the work. So, like I said to you, we have our baseline, which don't contain oversampling, and we have the approach 1 and the approach 2. Once again, let me reinforce the idea. So the approach 1 is the incorrect one. As you can say, we grab the original data, we perform the oversampling the entire data set, and then we perform the cross-validation. It is completely wrong. The right one is original data, we perform the cross-validation, we divide it in train and test, and only in the training we perform the oversampling. So in terms of experimental details, so at the time we use 86 data sets, 10 state-of-the-art complexity metrics, I will talk about complexity metrics later on, and 14 state-of-the-art oversampling techniques. Like I said to you, there is a huge variation of oversampling techniques and it is not very difficult to use. So regarding complexity metrics, let me only say at this moment that what are complexity metrics? These metrics basically evaluate the percentage of overlap in your data. What it means? It means that if you have a huge percentage of overlap in your data, your classifier will have problems in the classification. If, for instance, the complexity metric that says that your context is a low-level complex context, maybe your classifier will work well, okay? And typically, these metrics vary between 0, low-level complexity, to 1, high-level complexity, okay, in terms of values. So, this is the performance analysis of the two approaches. Let me remember you that approach 1 is the incorrect one and approach 2 is the correct one. As you can see, there is almost no almost difference between the training and the test here, of course. Why? Because you are replicating the instance in the training and the test. And in this one, the correct one, you have a huge difference between the training and the test, which proves that you are doing well. So in terms of conclusions of this work, of this part, so of course approach 1 promotes the optimistic results. The approach 2 is the best one to use, and of course, and following Luengo, a guy from this house, if you have a difference between 0, 1 in the training and the test, you will not have you will not have overfitting. And following this reference, we don't have overfitting in our approach. So this is a complexity matrix analysis for the two approaches. As you can see, the approach 2 indicates that there is more complexity in the approach 2 than in the approach 1. Why? Once again, because in approach 1 you have the same instance, so in terms of complexity of the approach, in the approach 1 you have less complexity, and in the approach 2 you have higher complexity. And finally, like I said to you, we use 14 state-of-the-art oversampling. And since we have those data, it is not the main goal of the work, but since we have those data, we will try to understand what will be the best oversampling technique. And we find out at the end that SMOTL and MW-MOT were the best techniques. And why? Well, we can try to justify because these two techniques has, first of all, a cleaning process, and they can weight the samples of the minority class. So these 2 points basically justify why these 2 methods are the best ones if you want to use it for oversampling purposes. So now let's reach the second work that is produced with Alberto Fernandes. This is my background here today, backup. So basically the idea is very simple, to explain at least. So many authors claim that imbalance per se is not a problem, because we have also some classifiers that can handle with it. But in combination with other problems, it will turn a severe context. So what will be the other problems? Well, we have some possibilities: lake of density, dataset shift, small ligents, and class overlap. What class overlap means? Typically means that you have an area in your data set or your data space if you want to, and in that area you have points that belongs to a class and to another class, okay? And why it is important? Because when your classifier tries to classify in that particular area, he will not have the possibility to understand well the separation between the two classes. But what is the problem here? The problem here is that we don't have yet a taxonomy that tries to characterize overlap. So the overlap can result in different shapes of classes, the amount of overlap between classes, and the proximity of two classes, and the number of informative sample available for training. So in this sense, we reach the data complexity matrix. For the first time, Hu and Basu proposed 3 families that are able to characterize the data complexity in what concerns to overlap. They proposed at the time like I said to you, 3 different families: overlap of individual feature values, separability of classes, and geometry, topology, density of manifolds. After that, many authors tried to propose their taxonomy for this context, like you saw in this slide, like you see in this slide. So in 2005, we have other authors that tried to propose other taxonomy, and in 2019, we have another authors that try. But as you can see, the variation of the families are very, very big. The number itself and the family itself. So our goal here is try to propose the taxonomy that tries to uniformize all of this information in once. So at the time we proposed this taxonomy to characterize the overlap, and we divided in 4 families: the feature overlap, the instance overlap, the structural overlap, and the multi-resolution. Let me tell you that the multi-resolution is a kind of the other family, because I do believe that it's not well characterized yet, but other 3 completely well defined. And what will be the process? Well, the process is very simple. We need, first of all, to decompose our field in different areas, and inside each area we try to characterize the overlap in that particular area. Let's try to illustrate a little bit with some examples. So feature overlap, family. So it is related to the concept of class separability and how it works. I will illustrate you with 2 metrics The F1 matrix is illustrated in that graph, and the F2 matrix is illustrated in that graph. So imagine F1 and F2, these are variables in your data set, right? And you have 2 points which belong to each of the class. So you have the blue X and you have the red dot. So the goal is try to project those points in each of the axes, and after that you understand what will be the overlap inside the axis, and then you characterize the overlap of your data. For the F2 measure, basically we want, first of all, for each of the variable, we want to define an area. And inside that area, we will understand what will be the percentage of the points of each of the class, and then we associate it with the value for characterize overlap. So now we have another family, instance overlap, which is correlated with local data characteristics, and typically for that we use KNN approaches. So imagine this example, imagine this, it is our data set, and I will grab 2 points in the random way. So I will grab this point here, and I will grab this point here. For the first point and for the second point, I defined a number of neighbors that I want to use. In this example, we use 6 as the number of neighbors. As you can see, to this point, the 6 neighbors that I selected belongs to the same class. So here, in this particular area, in this circle, we don't have overlap. So we are good. To this example, to the new one, you select the blue cross, you select the 6 neighbors, and as you can see, in the area of the 6 neighbors, you have 4 points that doesn't belong to the same class. Okay, so for this metric, we obtain the value of 4 for the second example. Structural overlap. Structural overlap typically is related to the concept of data morphology. And typically we use 2 types of structure. The first one is the minimum spanning tree. As you can see here, you have all the points of your data set, and you want to construct the edges and the vertex, okay? And the analysis is very simple. You need to analyze in the consequent vertex if they belong to the same class or not. If not, at the end you have the fraction that indicates the percentage of overlap. Another example, not using the minimum spanning tree, but an hypersphere context. So the concept is very simple. Imagine that you have this point, and you will construct by each point an hypersphere that is centered in the point, and you will increase the radius, okay? Until when? Until you reach other point of another class. So at the end, if you have hyperspheres with huge radius, it means that you don't have overlap. If you have hyperspheres with very, very small radius, it means that in the same area you could have different type of points. Okay? Finally, the multi-resolution, like I said to you, is a kind of the other family, but basically is related to the trade-off between global and local data characteristics. Basically, this is only one example of a metric. So we have some points, we create 3 hyperspheres, then we use a mathematical function to map the value to another view, and then we correlate the values in order to understand if we have overlap or not. But like I said to you, inside this taxonomy, probably the one that we need to improve is this last family. Okay? Now we will pass to the Jupyter Notebook to experiment a PyCol library that we develop in our lab, which contains all these kind of data complexity metrics, okay? In the Jupyter Notebook, we put a lots of comments. So it means that afterwards, if you want to use it in your research work, I think you will not have any kind of issues, okay? If you have it, please send me an email, I will try to help. Okay, so let's switch to the Jupyter Notebook. Of course, you don't need to run nothing, okay? Don't worry about it. So like I said to you, the PyCol library is, of course, a Python library that contains many complexity metrics that you can use, okay? The ones that you saw in the slides and more, of course. So how you can use it? Simple, you need to install our library and then you need to install a Python library to use. In this case, the imbalance learn, okay? So now we have tried some examples to illustrate some concepts. The first concept is the linear one, so it means that our library supports different input formats, so we support ARF and CSV, and to illustrate it, we use Iris dataset, and to see the classification of that specific dataset, we use a logistic regression and F1 score. So it is what it is. So it runs okay. So if you want to check from the Iris dataset perspective some overlap metrics, you can see that the majority of the metrics, the colors means families, okay? So the blue color means the feature overlap, green structure overlap, red instance overlap, and yellow multi-resolution. And as you can see, for the Iris dataset, the complexity that is indicated by the metrics are very low. So please remember that near to 0 means low complexity, below to 1 means high complexity. So as you already know, the Iris is a very simple data set, especially for classification. So it means that this metric represents our reality. Let's continue. So let's change it for a new data set, and we select wine quality data set. So in this data set, we characterize the quality of the wine using different variables. Okay, this is a binary data set. So in terms of instances, we have our majority class with more than 1,000 instances, and the class 1 we have 53. So it's quite imbalanced. So we run the metrics, only 2, that indicates that there is no complexity. And at this point, you need to have some thinking about it. You need to think about it. So we are in the imbalanced context, very imbalanced one, let's say, and the complexity metric says that there is no complexity. Okay, so could be wrong, could be right. Let's explore a little bit. So this matrix is the overall in all the data set, right? So let's explore it a little bit. So let's try to use random forest classification. And as you can see, the random forest fell in the classification of the class 1, which is the minority one. So I think we are good. These results is the ones that we try to predict later on. But now let's try to only calculate the oversampling metrics for the minority class, not the overall, but for the minority class. And as you can see here, the graphic completely changed. So the complexity metrics say for the minority class there is a huge complexity. Okay? So as you can see here, for the class 0, the values of those metrics are near 0, which means that we don't have complexity. And for class 1, yes, we have values almost in 1. Okay, now it makes sense. Now let's try to use SMOTE to perform some oversampling. So we choose another data set. We need diversity, so another data set, transfusion 1. In this data set, once again, we have an imbalanced context. So class 1 is the majority one with almost more than 500 instances, and the class 0 more than 100. So this is the transformation that we need to do. So in terms of classification, as you can see, the class 0 is okay, but class 1, since we don't have so many instances, is not so okay in terms of performance. So let's try to run the metrics, the complexity metrics for each of the class. As you can see, the class 0, it's okay. It has some complexity, but not so huge complexity. But for class 1, yes, we have almost 6 out of 10 if you want. So how we can live with that? Well, first of all, we need to oversampling. In this particular approach, I'm not a big fan of it. Why? Because typically, imagine in a real world. In a real world, you have imbalanced context, right? So in a real scenario, you will not put in the same level the instance between the two classes. So in the real world, if you oversampling, for instance, only 30% of the minority class, for me it's good. It's fine. So you don't need to put at the same level the number of instances between classes, because I think it's not fair and it's not representative from your work. So when you have an imbalanced context, please only oversampled 30% maximum, okay? But here in this example, we performed in the same level, the two classes, okay? So now we have the same number of instances between classes, and we will run once again the complexity matrix. As you can see, the number of the values of the complexity matrix, especially for the minority class, decrease a lot. So before we have 0.6 in some of the metrics, and now we have 0.3, 0.2, so decreases a lot. And of course, the performance also decreases, especially for the class 0. So for the class 0, decreased 10%, more or less, the performance of the classifier. And for the class 1, increases in 30% after the oversampling. So, which means it makes sense. Finally, one of the features that our library supports is a visualization, and I think it's very interesting. The visualization is based on, depending of your choice, is based on the PCA or the TSNE, okay? And with this visualization, you can easily understand the complexity of your data. So this is one of the representation using the TSNE, and in here you can see two things. The first thing is that we are using a scale of complexity. What it means that if your points are blue, you don't have complexity, basically. And if your points are red, you have a huge complexity. So with this representation, what you see, first of all, the class 1 has more complexity than the class 0, for sure. And you have many regions of overlap. Here, 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 etc., etc., etc. So you can see the complexity of the points, and you also can see the overlap regions. For the PCA is the same. Of course, the representation is not the same, but the concept itself is the same. So you can see the overlap and also the complexity. And if we return to the iris dataset, which is a toy example, right? We can easily understand why iris is very, very easy to classify if you check this graphic. Basically, you don't have overlap, I think. And also, the majority of points present the blue color. Means that there is no complexity in the points, okay? This is how you can justify why iris is a very, very easy data set. So it is for now to the imbalance world. Let's return to the PowerPoint and let's go to the missing data, okay? In a similar way, we can define missing as the lack of information in one or multiple variables, right? And why it is important to address such issue? Well, imagine that the goal of your classifier will be create an hyperplan that divide perfectly well the two classes in a binary context, right? So when your classifier tried to do the same thing with variables with missing, the classifier doesn't know if the dot belongs to one class or another. So you need to address it. So, but if you think in theoretical way, we can have different natures that result in a missing value. This is only 3 examples. So a physician did not record any information of a patient by mistake during his daily life. A faulty scale does not send some measurements to the central, and I will have a war here. Well, a lady did not answer a particular question in a questionnaire typically related to the weight or age. So as you can see, the nature of these 3 situations are completely different, okay? So in the literature, we have this kind of nature mapped in what's so-called the missing mechanisms, okay? So we have 3 types of missing mechanisms. We have the completely at random, and not at random. And what are the differences between them? Well, it's very easy to understand. When you have a missingness that is related to the completely at random, it means that the missing value is missed due to a random process, like a physician. He forgot for that patient, but for the others probably you will not forget, okay, to put. For the MARD, which is the missing at random, it means that that particular missing value is related to one other variable that is in your dataset, or in multiple variables that are in your dataset. It means that there is a correlation between the missing value and the other values of other variables that you have in your dataset. And finally, you have the MNAR. MNAR is the worst one. It means that the missing value, the origin of missing value is related to the variable itself, or variables that are not present in your dataset. Let's try to illustrate it with a practical example. Imagine this. Imagine that you have a dataset that is composed by only two columns, right? So the IQ column and the complete one. So the goal of this dataset is try to correlate the number of jobs performed versus the IQ of a person, okay? And our goal is try to simulate missing values in this column attending to the mechanisms, okay? This is our goal. So for the first mechanism, the completely at random, we randomly select some values of here and put missed. So there is no any kind of correlation, okay? So let's move to the other one. So the other one, MAR, means that we have a correlation between the missing values and some of the variables that are already present in our dataset. So what I did here is that for values of the IQ column between 78 and 87, I put in the complete variable all that values missed. So it means that there is a correlation between the missing values and the values of IQ column between 78 and 87. And finally, the MNAR. Like I said to you, this is a more complex one. So the MNAR means that the missing value is related to the variable itself, or variables that are not present in the dataset. So for the first attempt, I did it using the first formulation. So for values between 7 and 8, I put those values in missed. And for the second situation, I create another variable that doesn't belong to the dataset, and I correlate those values with the values of the other column, and I put it missed. So for the values of the new variable, the new column between higher than 60, I put all the values missed. So this is the difference between the three mechanisms. So we understand what missing value means. We understand the missing mechanism. So now it's time to know how to address missing values. The most popular approach is the imputation, which means that we replace the missing value by a plausive one. And how we can reach that value? Well, typically we use the same and classical setup. Well, basically we collect complete data from any source that you want, and then we synthetically generate missing values in one variable or in multiple variables, assuming different mechanisms if you want. And then we input. And then you can run your classifier. So you have two possibilities to quantify the error. The first one is to compare the imputed data set with the complete one, and you know the error of imputation. And finally, you also can know the degradation in the performance by comparing once again, your ground truth, your complete data set to the one that was imputed, and at the end you can know the degradation of the performance of your classifier. So you have, like I said to you, for the experimental setup, 4 steps. Please do not name the second one amputation, because it's not a good term. Some authors use it, amputation, but it's not a good term. Please use it like missing data generation, synthetic generation, things like that. So we reached the third work. And the idea of the third work is very simple. You know that KNN is a very simple algorithm, and typically KNN has some good results in some specific scenarios. We all know that for high dimensional scenarios you cannot use KNN, but in others you can use, and typically KNN ensures at the end good results. And how KNN works? Typically, they try to identify similarity between instances, right? And how it works. Basically, the similarity is based on a distance function, right? So the goal of this work is try to understand the impact of the choice of those distant functions in the imputation phase. Okay, so we are using KNN as our imputator. So the goal is try to understand the impact of the choice of the distant function in the imputation phase. So this is only a justification why KNN is so popular. It's simplicity. Well, it's a simple method, non-parametric, which is very important nowadays. It can handle both continuous and categorical features. It has been shown to preserve the original data distribution, which is important, and it provides high interpretability and explainability. So this is the overall setup. The setup that we used in this work is the standard one, and for the experimental setup details, we used 150 open source data sets composed by only continuous features, only categorical features, and a mix between the categorical and the continuous. In terms of imputation, we use MCAR mechanism, assuming different missing rates, 5, 10, 20, and 30. For KNN, we use 4 different values, and we use 8 different distant metrics. For the classification, we use CART. Okay, I will not pressure with the mathematical thing, but only to understand for each HEOM, so how this distance works. So if you are comparing two instances, and for a specific value, if one of those values are missed, they put 1. Otherwise, depending on the type of the variable that you have, depending if it is a categorical or a continuous, you will choose one of these formulas, and at the end you will have your value of similarity. For HVDM, the same, so 1 if 1 is missed, and if it is categorical or continuous, you have these 2 formulas. And finally, these distances were updated to attend if both are missed or not. And in this particular article, we also propose our metric. So you have another metrics here, Euclidean distance, things like that. So, most important, what is the take-home message, which is typically the most important in the article? For classification performance and for imputation. For classification performance, you see that the HVDM and the MR distance prove to be the best ones in terms of optimize your classifier performance. For the imputation, well, there is no clear pattern here. So you have, for instance, for the heterogeneous data sets, you have MDE, HVDM, SIMDist as good distance. For the others, you have SIMDistance for the continuous data sets and MR. For the categorical, MR, HVDM. So there is no clear pattern, but for the classification performance, yes, HVDM and MDE were the best ones. So let's come back to the classical setup. As you know, we started with the complete data set. Why? Because it will be our ground truth. And then we synthetically generate missing values, okay? Attending to if we want to generate in one variable or multiple variables, and also attending to the mechanism that we want to simulate. In this work, we try to grab all the strategies to artificially generate our missing values in one library. So we grab all the works that propose new strategies to generate missing values, relate to one univariate or multivariate, and attending also to the mechanisms, and we put in the library. And we have in that library 19 in the beginning. But the problem is, especially for Menard, the most terrible mechanism, we don't have good methods to generate. So in this particular work, we propose 3 new methods. So basically, for the first method, we propose, the strategy will be simple. We will identify the highest values or the lowest values, and then we decide the percentage and we generate the missing values in those values. For the second strategy, basically what we did was we create a new variable in our data set following a normal distribution, and then we with that new variable, we simulate the missing values in the variable that is already in our data set. And finally, we have the third method, which is a combination of these two methods. So now it's time to hands-on once again. Let's move to Jupyter Notebook and use this new library, the mDataGen library. Okay? So let me change here. Okay. So how you can use it? Simple. You need to, of course, to install it, and then you need to decide what will be your missing rate. Okay? In this particular point, missing rate will be 30% of your data set. Please be aware, this is the overall missing rate. I will not say here that the missing rate is being present in only one variable. I would say that overall, the missing rate will be 30%. Of course, if we generate only missings in one variable, it will be 30% in that variable, but could be in overall. Let's try to do it using iris. Okay? So this is the dataset iris. Now I want to generate in a new univariate way and using Mekar mechanism. So I need to define what will be the variable that we will generate the missings. And as you can see, we have 150 instances. So the code says that in 45 of the instances of the pedal width variable, there is no value. Okay, so overall, we have simulated 30% of the values in this particular case in one particular variable. So now we have a possibility to do an histogram. And this histogram is related only this variable. So it means that, imagine, in this variable, you have variables between 0.1 and 2.5. And this histogram means that, for instance, for 0.1 values, I generated 22 missings and maintain the others. Okay? So let's try now to simulate in more than one variable. We decide what is the variables that will receive the missing. And as you can see, for the same data set, these two variables, so we have 150 instances, and for these two variables, we only have 60. Okay, so the other values are missed. So if you do some math, you will see that in the overall, you have 30%. You have another kind of graphics that you can use, which for me it's very interesting to see. So the bar means the range of the values in your variable. So when you have false in the bar, it means that this value is missed, okay, in the range. So let's continue. So this is the histogram. You already understand how you can interpret these histograms. For the multivariate scenario with MAR, this is it. You need to, first of all, calculate the correlation. It is important. And this is the missing value of this variable attending to this one. The same here. And then we reach the imputation. Okay? So at this point, we all know how we can generate our missing values. Then we need to impute. So first of all, for the classification, we choose logistic regression because it's not our main point here. And for the imputation, we will choose three methods. Okay? So the mean, the imputation based on the mean of the variable, we obtain this square error. So 0 is the best one. So then we used KNN to impute, and the mean square error dropped. And finally, we use MICE. MICE is a kind of state-of-the-art imputation method for missing values, and the mean square error also drops. But once again, as you are living with data quality, you need to understand if these values are real or not, and you need to know how to interpret. Let's try to understand what are the changes that MICE did in our data set. So our data set, basically the iris, has three classes, as you know. This is the points of each of the classes. So you have the blue dots, the orange X, and the green triangles. This is the distribution of your points, of the original data. And let's check how MICE transform your data. Basically, listen, here you don't have basically overlap. You have only overlap in 3 points, 4 points maximum. And after you impute your data, generate missing values and impute your data, the distribution of your points is more or less like this. So this class is completely different from the beginning, and this point also has some differences. So this is it from the Jupyter point of view. And I conclude. Thank you very much.
Thank you, Pedro. Thank you very much. Questions? Alberto, please.
Thank you so much, Pedro. It's always a pleasure to have you here. You know that I am really into this kind of works. We have collaborated, fortunately. And I was wondering about the overlap. Mm-hmm. Because at the end of the day, it seems that the overlap is mainly based on two issues. And I want you to make a reflection on that. One is about the feature space. Mm-hmm. I mean, if you are using kernel trick or you're using neural networks, you can create ASC variables, and in this new feature space, you can avoid somehow the overlap, and therefore the problem could be solved or not. And the other, and this is the thing that rings me a bell with your talk, is about wrong labeling, because it could happen most of the times that we trust standard dataset repositories, and we measure the overlap, and this dataset is overlap because this and that. But it could happen that most of the times it can be also due to wrong labeling, and therefore the problem is not so much, but the question is how data is collected or labeled. These two issues.
Okay, so the first issue is that from the literature, we all know that imbalance is a problem even for deep techniques. So this is all validated. It is already validated. The overlap in the combination with imbalance will be even worse. So I don't have an answer for that, for the first question, but I would say that we need to somehow improve the characterization of overlap in terms of metrics. Now we have some metrics, but they present some erroneous behavior in the calculation, especially the multi-resolution ones. So I think we have some work to do in this particular area. So regarding to the second one, the erroneous data, right? Kind of. Yeah. Well, first of all, if we are living with a private data set, we need to guarantee that the collection has been performed well. If we don't know nothing about the collection of our data, we need to curate our data in some aspect. So maybe we can, for instance, use LLMs in order to understand what will be the most frequent patterns in that particular context, and try to somehow compare if those patterns are present in your data set and what are the patterns that are present in the data set that, for instance, the LLM did not mention. So I would say that data curation could be a possibility to increase and to guarantee the trustworthy of your data.
And data curation with LLMs is something that also links with the topics we are discussing. Yeah,
of course. Could be a possibility.
Yeah, thank you so much, Pedro.
My question is totally naive. You have been talking about 100 problem related with the data set, so missing data set overlap and so on, 100. So my naive question is, in all this theory, what is the state of the art of the math foundation? So in what part of all these problems we can say that there are more consistent and deep, pure mathematical theory behind?
Okay. Let me try to, well, I don't have a huge knowledge about it, but let me try to point some directions that we need mathematicians to help. As you can see, in terms of missing data, we are using a very controlled setup. What it means that we started with a complete data set, then we generate missing values, etc., 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 in order to have the ground truth. But for instance, in a real world scenario, you will have a data set that already has missing values. So my point here is that how we can, well, in the best scenario possible, we will identify the mechanism behind the missing values, and then I will impute accordingly. But how can we detect the missing mechanism? This is a question for a mathematician. We have three mechanisms. One is completely at random, so it's a kind of exclusion, okay. But we also have the other two ones. The one that has a correlation between variables inside the dataset, and the other that presents the correlation outside the dataset. How we can, mathematical speaking, detect those mechanisms? This is a question for a mathematician. And I don't have a question, of course.
But Pedro, also you have the topological data analysis for
Yes.
question the complexity.
Yes,
Also.
yes.
There have been recent works that focus on, as you said,
this is the first example, and the other example will be that one.
And people work in topological data analysis to analyze the difficulties of a given data set.
Yeah, let me add some information. For instance, I present data complexity matches for overlap for tabular data, but there is also exists this kind of metrics for images. So there is a huge path.
So they have topological arguments, set theory, and all these things.
I'm not quite into it,
Okay.
but I have heard, and indeed there is one colleague of us, one PhD student that comes to the Master of Data Science to provide a talk in topological data analysis on the 6th of March. So I can provide an announce. So if you want to come.
Sure.
We create a new topic of research of marine current right now. Right now, we are creating a new topic. What about?
Have you compared the performance of the imputation methods you present with new approaches such as prior fitted networks? The PFM, the model released last year, can also impute data?
No, I'm sorry.
Okay.
Go for it.
I have a question. So thank you for the talk, and I want to ask if what do you think about generative models based on deep learning like GANs to address the task of unbalanced data for oversampling? And so yeah, basically it can be some problem for the quantity and the quality of data if you are using these generative models, like features overlap or scarce data quantity on the minority class. And I also have another question about before you said that it's better to don't oversampling too much, so don't reach the same amount for both the classes. Is more a problem to something to keep the real dynamics of the original data, or
Yes.
Yes.
To maintain the real world properties,
Yeah.
I think.
Okay.
This is the answer for the second question.
Yeah.
For the first question, well, you have the generative AI is present in our daily lives. But one of the problems that I typically pay some attention is that, okay, you have now many possibilities to generate data. But at the end, that kind of data represents a specific context, yes or no? I don't know the answer. You can, indeed you can generate a huge amount of data, no doubt about it, with LLMs, etc., etc., etc. But at the end, for instance, in a physician world, I can generate a huge volume of tabular data or even image. Those images are real, are possible to be real. If I put an image generated by a diffusion model and a real one, the physician will detect the difference, yes or no? I give you an example. We are talking about missing values and missing data and imputation, right? But typically for tabular. But imagine this. Imagine that you will expand the experiment for image. And the image you don't call missing data imputation, you call it inpainting. It's the same. Okay? Imagine this. Imagine that I'm using breast cancer images. And for some reason, 20% of the image is gone due to some practice in the acquisition. Okay? And I want to somehow don't repeat the exam, and I want to reconstruct the image. At the end, the image that I reconstruct is a valid one for a physician or not? This is the question. The image reconstruction follows the anatomy, follows the artifacts that a breast image has. I don't know. So you need always to validate the synthetic data that you generate. If it is tabular, you can use, for instance, the distribution of the data, the frequent patterns, among other things. For image, it will be more complicated, but you need to find a way to validate.
Okay, thank you.
All right. Any other question? So from my side, I'm going to go as usual with a more philosophical question already. So in your work, you've been showing us and telling us how cool is to go with a data-centric approach, right? But what you've shown here, if I recall correctly, you've been showing on, let's say, traditional fixed-purpose AI systems, right, in which you have one classifier for a particular task. Mm-hmm. So I would like to know what's your vision on data-centric for a general-purpose AI system.
Okay, I already think about it a little bit. In terms of imbalance, I don't have an answer for it. But in terms of missing, let me say that we are finishing a work that we are using LLMs to help in the imputation. And I must say that the classical methods outperform LLMs, no doubt about it. And I think I know why. Because, okay, LLMs are training with a huge volume of data, impossible to fight against. But the question is, when you have a new data that LLMs never saw and don't follow the same distribution that LLM are trained to, they will miss, completely miss. So, like deep learnings, LLM are good for some contexts, but completely fail in others. So, I think it's a kind of technology, right? When we have a new technology, we have a huge amount of paper saying that it will solve all of the problems. Then we realize 1, 2, 3 years after that sometimes we cannot use it. LLMs will follow the same, but probably in the future we will have
But I think LLMs, you're very right, but they are too general purpose for missing values imputation. But I'd say, and I go a little bit with Oroel's point, if you were to use a transformer pre-trained on that task of missing values imputation, you could use that PFN possibly to do the same thing. And,
the question
I don't know how competitive that is compared to anything else.
The question is the computational demand to train a transformer, first of all, and the time that you have to impute. It will also be an issue.
Well, the inference, I think it will be real fast.
The inference, yes.
The little problem with
the little problem with the training.
Juan, please.
I have a question, but it is for the both of you. It is not for.
Okay, I will
fight.
Now we are talking about general purpose systems. It comes to my mind the Peter lesson where it says that the more human knowledge we include in a system, the worse it will perform. And now we are talking about data-centric AI. Do you think there will be a moment where all the knowledge and all the data that a model consumes, it is generated by himself? Do you think that we could reach that general purpose system with that approach?
You're the data-centric guys, yeah.
Yeah, but this question has no answer. So, well, the answer is we will see. But let me tell you how we did it in the imputation study that I mentioned. So, in the first phase, we asked LLM to give us 10 data sets of healthcare. Then we asked LLM to artificially generate 10 data sets. And then we create our own. Okay? So LLMs, in terms of performance, in the data set that they generate and the data set that already knows, perfect, well, fine. But in the others, fail completely. So, well, basically I don't have an answer for the question. We will see. But I think in terms of validation, I think we will need the validation at the end, somehow. It's for sure for me.
Yeah, for me, and in my view, and I aiming to answer your question, I'd say a data-centric approach is very much needed for any general purpose AI system. At the moment, the way they're doing it is they're feeding in everything, and then we do some reinforcement learning to repair all the issues with the data, because the data might be biased, because basically there is more data about particular things, right? And the model actually learns that. But if we were to use techniques like oversampling, undersampling, pre-processing and stuff like that, you could probably help mitigate that a little bit in the model. That's for sure. But at the same time, your concern was more about, okay, now the systems are able to generate data. Should we continue using that data to feed that back without us in the loop? And my answer to that would be, please don't do it.
Yeah, sure.
Because in my experience and what I've seen, and there are already papers talking about it, that they say they will degenerate to something real bad. It will not work eventually. So reinforcement learning, the human still needs to be there from what I can see. I don't know if maybe at some point we get so good that actually they don't really need us, but and not yet.
In AlphaGo, there was no human intervention in the end. It was only about reinforcement learning, about data generated by the own model. So that was my point. There will be a moment where the human knowledge that we have embedded by the text and the enormous corpus or the internet we have, they will be not sufficient or will be not enough quality to truly make a general purpose.
Yeah, but please do not forget that in real world you don't have perfect data. Please don't forget it.
Yeah, it's a good point. We don't know what's going to happen, right?
Yeah.
My guess is not going to be that easy that we're going to run out of data, because we humans still are able to do more, right? It's part of the discussion we had yesterday as well, right? So we end up having better tools. So now maybe we write other stuff that were never written before. So it's new information, right? Or we collect different kind of data because now we can do it in a different way. So I don't know. I don't think it's going to stop just now. But maybe in 20 years' time, who knows? You will be giving talks somewhere about this.
It will be the 20th edition of the Winter
The
School.
20th edition, yeah.
And
I will be the 60-something-year-old. Any other question? We are doing well in time. Danny, please.
One question. Very nice talk. Thank you. And the question is, when you have overlapping classes, when you are in real world problem, what is your strategy? If I decide that there are very overlapping classes, which is the not solution, because I know this means that it's very complex problem, but which is the approach we can use to get a better result? In my opinion, if there is not overlapping classes, maybe the underlapping and overlapping maybe could be easier.
Yeah.
But in that case, which is the alternative to afford this to tackle this type of problem?
Yeah, I think there is no alternative, but let me tell you one thing. When you are at a big dimension problem, the problem is to identify if you have overlap or not. Because, for instance, in visual terms, you can only validate with 2D or 3D. When you go to 4D and D, it means that I can see, for instance, 2 points here and can be overlapped or not. I don't have sure. So this is could be a problem for a mathematician to solve. But basically is that if you can visualize, you can validate if there is an overlap or not. But in any situation, it's very difficult to understand if there is an overlap or not. First of all, you have a problem of characterization. But yes, if you want to somehow guarantee something, maybe the oversampling, things like that could be a solution. But once again, you don't have 100% sure what happened in that ND world. It's a problem.
Great. Wow. We're so well in time that we're going to have to wait for lunch. I think lunch will not be served until 1 p.m. I believe. I will try to speed things up, but I don't know if that will be possible. So let's hang around. Maybe you can even go to the posters. You can continue talking about research if you want, but you can also talk about other stuff. Otherwise, I'll see you in the restaurant at 1 p.m. Okay? Thank you very much. Thank you once again. All right. Afternoon. Good news is only one more talk. Sad news is it's Iván. No. Oopsie. Oh shit. I did it the other way around. No, it was the other way around. Sorry. I'm dyslexic.
It was the lunch.
Sorry, the lunch is too heavy. For the very last talk, we've got one of our very own from here, from Granada. He is Iván Sevillano García.
Correctly, but yeah.
Nice. I pronounced it correctly, I think. And he's got also a double degree in math and computer science, right? So I think the talk will be a lot of math as well. I'm hoping, or maybe not, who knows. But what I can tell you for sure, I will not be the type of person explaining what he's talking about. Because I don't do that type of AI, right? So you do. So hopefully we will understand something because he works on explainability. So please, Iván, take us away. Hopefully you.
Wow.
3 hours only. Okay?
3 hours only. Oh, maldita sea. So yeah, I'm Iván Sevillano García, like a PhD since November here in Dusty building. My PhD was about explainable artificial intelligence. The thing, someone told me about the X, why the second X is the one who is, it's because it's cooler. I mean, XAI looks better than EAI, you know. So yeah, here in Dusty Institute, we are part of all of those people and many more. And we do several stuff like having a Christmas tree over there on Dusty and so on. But let's talk about what we are here for. Explainable artificial intelligence. Why would we need it? I mean, let's say we have artificial intelligence made for spam detector. It made as an spam detector. Do we really need someone to explain me why this is a spam or something? I mean, I just wanted to. Or for example, if I'm playing a video game, why would I like or need someone to explain why an AI on the video game is fighting me better? Also, coming back to generative artificial intelligence, actually, if an artificial intelligence made up some stuff, some information like Cloud, ChatGPT, or made up an image like the one I made with Link and Zelda over there, the only need of
You forgot to mute that.
So do we really? The only thing we actually need is that this is made up from an artificial intelligence. In other cases, like let's say someone is taking our CV by an artificial intelligence tested, our cancer or radiography is tested by an AI, or maybe this is a Spanish new I'm going to talk about. The Spanish government has firstly they actually made our supreme, let's come back again, the code of an artificial intelligence who decide who has the right to have help or economic help. Is needed right now in Spain to be transparent, at least. What does it mean? Well, we'll see about. But this is an actual news about that. On those three cases, maybe we need more than just knowing that an artificial intelligence has done a decision. And of course, there are also other kinds of artificial intelligence that actually I don't even want to be explaining why my government is taking into account. Where am I, for example, which other countries are doing. So all of those cases are actually took into account on the AI Act on 2024. Do any of you knows about what is the AI Act? Some? Not really? Well, okay. The thing is that they developed like several cases where artificial intelligence is evaluated in terms of risks. The examples I put before are actually like on those specific cases, like where I don't care if it's an artificial intelligence who's doing nothing. If I need that the generative model give me that what they are making is actually made from artificial intelligence, which is the limited risk, or if we don't even want to an artificial intelligence to do this job. But the need of XAI is concentrated on just the high risk case, where if I get more money from my government or not, because an artificial intelligence is deciding that, or if maybe my doctor gives me pills or several kind of other stuff or so on. So the explainable artificial intelligence is not for all of the artificial intelligence. It's just for those cases. So, key terminology about explainability. There are 3 terms over there. Do any of you know the difference? No one.
They are the same.
That was my first thought about. They look like the same. Like, yeah, everyone in the news or something, or even people who do talks like, well, transparency is something. Okay, I made a metaphor helped by maybe ChatGPT. Okay, sorry about that. It's not that. But actually, for me, it made sense. It makes sense. Transparency could be like, we have an algorithm, like a house. This house, if it's completely transparent, crystal, we know, we can see everything, what's inside. This is kind of transparency. At the end, if we have logistic regression, if we have random trees, but also decision trees, but also if we have actually neural networks, they are transparent if we have the model somehow. I mean, we may see what we're having. This is where the second term comes about, interpretability. We may have like the whole building seen from the outside. We know how we may see how they are behaving, but for the interpretability terms, we now kind of discuss like maybe a logistic regression or trees are more interpretable. They have like a map over what they are doing. And this is where maybe neural network is less interpretable, even if we have like the whole map of our artificial intelligence. And the third one, even if we have a plane, like a whole information about the explainability is more focused on real reasons. Let's say, let's discard, like maybe on this plane, we don't care about the park over there, just focus on the important thing. This is kind of at least for this metaphor, could be like if my house breaks the door, somehow, maybe it's because the alarm, I have some people stealing something on my house. So we know about which door is and when. Let's say focus on the thing. We don't care if my fridge is okay on that moment, like we have in the whole plane. So those 3 terms. Also, let's talk also about categorization of different XAI algorithms, or how do we differ from those. And I differentiate actually on those 6 ones, but there could be even more. Of course, we'll talk about. First of all, I'd like to talk about the local. When we talk about the scope, maybe we could talk about the locality of the explanation, which means I have one local example and I want to explain this specific example. Like here, like the red cross is kind of explained by this linear function separating kind of where the red and the blue zones are about. But also, we may have like a global scope where we have like general features, how they behave in the whole data set or in the whole space we're talking about. And there are also other stuff like kind of mixing it. And I really like those ones. This is an algorithm CRP. We'll talk about that later. But it's kind of mixing from local to global. So the categorization about scope. Also, it's not the same explaining as even here we look, well. When we talk about in data specific, I want to say that even if explainability could be made from algorithms, like really general, at the end, we're not explaining in general. We're explaining for certain cases. It's not the same having a tabular explanation, and we would like to have like some kind of things like that, like each tabular specific has several importance. Or in images. I mean, with maybe, from this point of view, it's not the same having segment 1 has less important or more important. We need something specifically for images at the end too. Even for data scientists or mathematicians, we don't care what about, but we need to focus also. And also the same with text. It's not the same. We could not use this kind of visualization for explaining those stuff because, again, we need to focus to the data-specific scope. Also, when we talk about algorithms on explainability, we may have a differentiation between model agnostic and model dependent. Usually, this differentiation, it's more about which information do we have about the model. And the black box model, even if we have the model, we want it to behave like a generic function. However, if we know everything about what's inside the black box, now it's a white box, we may use another kind of, we may have like more information. Also, those have pros and cons at the end. In the black box, we have like more computational time, and on the white box, we may have like really fast computation. At the end, we know, talk about that later. Also, it's not the same, and this is kind of, it looks like the same than the data specific, but at the end, when we talk about the result, what we're having, we may have several stuff, like for each specific feature, we may have an importance, we may have a relevance, we may have just heat maps as we have with gradients, or we may have rules. It's kind of more general. At the end, this is like a globalization point of, a global point of view of the whole problem. And also, not just about the result, but about the intention we may have when we have an explanation. We may, this is a new terminology about explainability that I really have to say that I liked, which is the red versus blue XAI. The red XAI is more focused on making artificial intelligence better thanks to human or experts' knowledge, or the biasing. But blue XAI, and that's why I like the human point of view, blue XAI is more focused on, okay, I got the final explanation, the perfect, not perfect, but the scope, the result of my explanation. However, I need my grandma to understand what they're having. So making it more explainable to people who's not talking about, who's not expert on the field. Also, another categorization, and I'm sorry about the categorization, we'll tell you about that later. The obtention of the explanation, you may have it by perturbing the original example. We may have also, again, gradients, which is different because when you perturb an example and see the difference between models, you may have an information. However, you may have also the gradients from the specific model, and it's kind of better. Or also having a sample differentiation, like we have this example here, which is an image, which is considered, I have it, that later, a war plane, and this would change the prediction by blurring this part, which is like the explanation. Then, after all those stuff, our categorization, any of you know like a general idea of what is an explanation? At the end, there are 6 categorization different categorization about what they could be. any of you have like the, well, this was actually, it was a question after my 50 minutes thesis defense, like, okay, you made everything about what is an explanation. And this was my face when they said that, because at the end, I mean, I'm talking about how to represent them, which features are important, are sample-based, are actually, my face was that because I had no answer to that, because what I actually was talking about, it was more specific thing, local linear explanation. This is a mathematical thing at the end. What we're talking about, this is like the first paper we talked about explainability, which is the Lime paper, like, why should I trust you? And what they define is just an explanation would be just a linear application which comes from the same place, from the input space to the output space, and you linearize it, or maybe logistic on a logistic way. Maybe you could change this function by another function or so on, and you have like this decrease of complexity, so you can, at the end, understand it better. At the end, this is a linear regression. So, local linear explanations, how to obtain them? Well, if you remind me about, if you look for the, one of the categorization we talk about is the model agnostic one. Lime, the first local linear explanation proposal, was proposed as a model agnostic, which means that they don't know nothing about the inside of the function. So what they are doing at the end is having this simple, really simple problem of optimization, where you have the difference between the model and the linear application, and you minimize it with a neighbor importance term over there. And this is even, maybe it could surprise you somehow, because even if the formulation of Lime and Sharp, two of the most important model agnostic explanation terms, explainability algorithms, are made from different theories, both of them are actually made from the same linear regression problem, optimization problem. The only difference is the pi x, which is the how long they consider whatever you have neighbors and a different neighborhood that you are minimizing there on the space. Organize how separate are the samples you're taking into account. And actually, when you have this sigma online, which says at the end, you want to parameterize how long are you looking for into the neighborhood of the samples. Sharp also has, I want to say that even if Sharp has like the same behavior, like the same kind of knowing of neighborhood of locality, Sharp at the end has the same importance on the whenever they have like the farthest example, they are also important. Okay, I was talking about neighborhood also, about a model agnostic local linear explanation. We may have like different concepts of neighborhood. On tabular data, on vectorized on Rn, we have like actually, you may consider neighborhood just by moving a bit the sample you want to explain, and then you have those samples that you have for the linear optimization problem. This is really simple, tabular data, vector value. However, if you want to use it on text, you may have to use another concept of neighborhood. For example, you may change the negative, the sense of some adjective too, and also the noun too, to produce synthetic neighborhood. However, also in images, the one that has been done by Lime at first stage was like occluding several parts of the images, and there you have the neighbors there. So let's focus also again about when we're talking about local linear explanation. The Lime one was model agnostic, but if we consider, like with Taylor decomposition, for a general function, we may have like an f, which is a function f, which is our model on a specific sample, and we may have the Taylor decomposition on this specific point. And you may have this decomposition where we have like the first term, the f on another point close to this plate, maybe the differential, the gradient, the derivative is not, thanks. The derivative and also an error and a square error about the distance about there. So at the end, we have g as the best, the derivative is actually maybe the perfect linear, the best linear approximation you have close to this sample. And each of the terms of the matrix A sub ij, it's actually the importance for each from each input for each of the output. So this is quite simple. We have a derivative, which, as we have the composition tailored, we have the derivative from an original sample. We don't care if it's derivative. We may have a gradient over there. So this is actually all of the algorithms that are made up from integrated gradients, saliency maps from the output to the input. It's just the derivative at the end. They made some integrals about the derivative or so on, like a chain of way, but the main thing is that you have the derivative over there. This model-dependent local linear explanation, at the end, we may consider, if we have a linear regression, we finally have like the A is the explanation we have, because we have the derivative, which, forget about the B, the A, the matrix A, is actually the main explanation. Also with the sigmoid may be a bit different, but also for other known algorithms, for other known models, like the generalized additive models, we have like the summation of several functions on each of the features of the space, and each of them has the importance, like we may differentiate between the importance because each term is only the importance of each feature for each of the points. Also, talking about the gradient-based ones, as I said, this is the same one. I mean, the grad counts at the ends are derivatives on specific terms of the convolutional terms, of convolutional models. And saliency maps are actually the real derivative from the input from the output to the input. Also, more general algorithms like the attribution-based methods, the main one, layer-wise relevance propagation, has actually this specific, instead of taking into account the derivative, it has the concept of attribution, which at the end is sharing making the derivative like step by step, but instead of making it from each layer to the next one, you're sharing like 100% of importance. So at the end, it's not the real derivative, but the 100% of the importance of the decision. And I want to say actually that the next step of layer-wise relevance propagation, if we take into account about the concept-based ones, what we're doing what we are considering is, okay, each part of the network actually has like different, different concepts. So if we take into account about a specific layer, like I only want the gradients who comes from this specific feature and delete everything else, we have like a concept, like let's say I concept over here. It's not for like separating the concept of each one. Also, I have to say that those ones, layer-wise relevance propagation and concept-wise relevance, are not useful for transformers because at the end the transformers dilute like spread the importance about the whole image from each step, but we may have like the important the concept-based on the attribution-based methods because of the locality of the convolutional neural network. Okay. After talking about all of those possibilities of local linear explanation, we may have considered like okay, here we have like the attribution-based method, layer-wise relevance propagation, concept-wise, attention layer-wise, which is a generalization to transformers of this specific algorithm. But which should I choose? At the end, we don't have more as humans at the end when we see an image or we see a feature explanation or a tabular data. We don't have like we may have an intuition about which one you prefer, but we need to measure it. And another important thing is that we don't have like the correctness of the explanation. We may have the intuition at the end. So for those stuff, this the first paper I'm talking about one of mine, which is Rebel, which is a framework I made up with several metrics and several considerations about generation of local linear explanation, about how good may be an explanation. And I like to separate between those two different considerations, which is my explanation a good representation or approximation of my model? Or the second one, which is actually G a good explanation by itself? A good explanation, or let's say what we're talking about. The three first measures are really simple to understand. I mean, if we consider the difference between the point I want to explain, imagine we have F, this separation between this space and this other one. If we evaluate on this specific sample and we compare to my evaluation, my explanation output, we may have like this difference. I like to say that C is a term specified to make this measure exactly 1 when the F and G are the same, and exactly 0 when they have nothing in common in a probabilistic version of it. Also, we could actually generalize to we have a neighbor on the same. This is the local fidelity measure is a generalization of the previous one. We have a synthetic neighborhood, and we measure how differ G and F, the explanation and the model. And also, the most interesting one, and actually the one that gives us more information about how differ are each linear, if we talk about the linear approximation, each linear application has itself a proposal of projection of the model, the element we are explaining. The projection is here, and we are proposing, this explanation is proposing the closest, at the end, the closest sample on the feature space to be the fear from my own decision. So again, we are talking about how much do we differ on the blue point over there, on the proposal, of the projection proposal of the local linear explanation. Also, talking about the second kind of explanation I'd like to, of measures of explanation. Taking account an explanation as a linear regressor, we may have like the expected, the importance of each feature. So for each vector of the matrix A, for each feature, we have like the whole absolute importance at the end, when you sum the whole importances of each feature, and we have the absolute importance. So how would we consider if something is concise enough? If we have an explanation which takes 1 hour and a half or 2 hours, it may not be concise enough. But if we consider just 20 minutes compressed, this is actually a concision. So what I'm doing with this measure at the end is exactly that. If we have a compressed information, we have more, we are concise enough, but if everything is the same importance, if everything has the same importance, at the end, it's not concise enough. Also, as we are considering different local explanation, the second measure we proposed on this paper is robustness, which is not an evaluation of an explanation itself, but about the proposal of our method. Lyman Shab, or as they are stochastics, maybe they give different explanation over different iterations. So what we're measuring there is the expectation similarity between two different explanations made up by the same proposal. So this one measures the angle, this one the difference in model of the explanation. And actually, there are many more. I mean, when I published it in 2023, there was also in the same year, Quantus was also made up. It was a library about measure, and there are many other like how faithfulness. They have monoticity, the local Lipschitz estimator. You probably would know. They estimate about the local Lipschitz, but I want to focus that those measures. Some of them, I like them, but why do I like them and why I prefer Mainz? No? Because Mainz is not just emotional, okay, I have to say. And the Mainz are actually measured from 0 to 1, but the robustness, because it's measured from -1 to 1, because at the end an explanation could be like in different directions, so this is completely okay. But some of them, like the local Lipschitz estimate, is a real valued measure. At the end, the Lipschitz estimator may be really big and so on. And I really like to make the measures like differentiable and also from the compact at the end. Compact means from 0 to 1 at the end because you measure. And that's the. I want to take, if you want to use another measure about that, another measures, take into account those stuff when you want to compare. So, again, after talking about local linear explanation and answering Pedro Garcia, which was the one who gave me a question, is this actually the explanation? I was talking about local linear explanation. Well, no, there are other ones. I'm every time talking about a local linear explanation is a linear application, but there are also example-based explanation, which it's kind of, instead of giving you a function which gives you importances, we have explanations by proposing you samples from the data set or made up samples. For example, there are considerations about the prototypical based explanation where we, as an explainer, we have an explanation that we have this decision made because those examples I have on my training data or test data, validation data instead of, is close enough, or we have several features like we have here. I really like this paper about understanding the extraordinary, which is the first time I made up that you may talk about data actually. We have the red color feature, we have the feeder feature, which actually is from our own training data, and you actually, the sample you're giving to us is actually quite similar. And somehow you may have those prototypes, which at the end makes the decision easier to understand by compression. Actually, also, there are like other kinds of, like, talking again about the projection of linear approximation and giving you an example, which is in the border. Another kind of explanation, instead of giving you the border, is giving you a sample which is really close to our prediction, but in another way different. So, like in this sample, wherever we have our plane over here, predicted by a model, the first explanation may be like it's a world plane, but because I don't care about everything there, but the features are those. And we give you, like, as a counterfactor, the blurred part of the main important features is blurred, and now I think that this is a hummingbird. So this is kind of another proposal of counterfactors. And also neighborhood-based. And this is where I'm going to talk about the paper. If any of you were on Monday, yesterday, yeah? The paper I published on Sunday. A reminder, here in Dusty we have a tradition. Every time you publish a paper, we bring, do you know what we bring in that? Okay.
Are we doing it now?
Not today. Maybe tomorrow, but because it should be more. Let's come back a bit as I'm going to talk about the StudX proposal. First, I want to introduce like a little bracket of what's out of distribution problem, out of distribution detection. At the end, it was in the other, okay. Out of distribution detection is formulated as simple as that. Wherever we have a new sample, x prime, from the feature space, is it actually take it from a random variable, which is the distribution one? Like here, it's really simple to say. Is the orange one part of the blue points distribution that I've been extracted and where my model has been trained? Right now, it looks like really easy to say no. Also, a little definition, when we're talking about feature space, at the end, we don't actually care about what is the input, because we may have like a feature description, a neural network, an extractor at the end, talking again about Banach space, if we have the projection over a feature space and so on. And from this place, we may have the final output used by the classificator or the. So whatever, every formulation, I'll be talking about this. So there are, just to tell you a bit about this problem, there are several proposals at the end. It's not me, the one who discovered the problem, and neither proposed like the first known algorithm. Talking about the feature space, we have several proposals. And actually, for example, Arantxa over there also made up a Mahalanobis distance proposal too, which is a parametrical way of thinking about the out-of-distribution spaces. Or also non-parametrical ones, like Cannere's neighbor, which actually what we measure here is, on the parametrical one, distances to the Gaussian distribution, if each of the classes we're having on the classification problem over here is distributed by a Gaussian one, this would be like a proper distance on this space on the classes. Also the non-parametrical one, instead of assuming Gaussian distribution on the feature space, we just take care about the nearest neighbors instead of assuming a certain distribution. But both of them, they are looking for a threshold. So we have a score, which on the Mahalanobis distance is the distance, the Mahalanobis distance defined out there, And the nearest neighbor is just the distance you have to the k neighbor. And you need to look for this threshold. From my point of view, this is kind of that you're, let's say, making up this, this threshold is kind of manual. Because, and even though if you have this threshold on the, after considering the training set, or the training set and also other validation sets and other out-of-distributed test set, your proposal may be like made up for those specific out-of-distributed data. That's why what I proposed actually is an hypothesis test instead of looking for this specific threshold. It's more relevant because it has this percentage. Why are we talking about this? We figured it out in explainability. At the end, what I am doing, the whole algorithm, I want to say that much about it, is that we have the model, we obtain the features, we have the sets of features, we consider distances between the sample we want to say if it's or not an out-of-distributed sample. We look for the nearest neighbor and measure the distances between the model, the sample, and the nearest neighbor. And again, the distances of the nearest neighbor to their nearest neighbor and compare the distances. So the hypothesis about that, the hypothesis that we're going to take into account is if those distances are different, are bigger or not. So that's the way. With the null hypothesis and the significance value, we may differentiate statistically on a more robust way instead of looking for a threshold to the difference between all of those. We may consider different distances, like we may consider distances between a sample and each of the different classes we have on the dataset. We may have the distances from the sample to the whole distribution of all the classes, or we just only take into account the distances between the specific sample and the class being predicted. At the end, this is more useful, because if we have an in-distribution sample and it's predicted correctly, nice. But if it's not predicted correctly, but the distance on the wrong class, at the end we prefer it to be considered actually an out-of-distributed class. So to specify about those stuff, whatever we have to formalize a bit. We have like the x prime and several samples, x1, xn, on the extracted from a random variable. What we are doing at the end is comparing the null hypothesis about the distances between the k nearest neighbor on x prime and considering we want it to be less than the distances, or less or equal than the distances we have to the k nearest neighbor of its xa. And the null hypothesis, the contrary hypothesis is the other one. So for testing that, we use the Wilkinson-Whitney test because it's a non-parametric. We don't need to assume anything about the distribution of the samples on the feature space, and that's the thing. So I really want to do it this one really fast. Just to tell you about the results, we compare it on OpenOD benchmark, and considering that this is the accuracy we have considering not detecting out of distribution, we have a really robust one, really robust results, and also taking into account like the hardest, it's actually the hardest data set, which is the considering vision transformer on the classification of ImageNet. We are actually the state of the art on this sample. So yeah, why are we talking about StudX? Because we are not doing just only the statistical test on the out of distribution on the out-of-distribution problem. But what about the X? Yeah, and here is where we consider also the neighbor-based, the synthetic-based algorithm. Whatever we have here, again, the feature space, we may consider the several nearest neighbor. Here, if we have here like the original sample, we have also the nearest neighbors, and on each of them, with other algorithms like the concept-based, the layer relevance propagation, other stochastic integrated gradients, or so on, we can separate the top n features, which has the decision over our sample. So wherever we have first approach and the top one feature importance feature, it should be consistent among the visualization, among the human part of the sample. If not, what we are doing is random, really strange correct model. So yeah, so that's actually the explainability part of the model. Why it is important and when to use it. Wherever we have a sample, an out-of-distributed sample, and we say this is an in-distribution sample, we may have this explanation considering like, yes, this is a shark, because look, the features I've noticed are actually consistent and robust on the training samples or in the whole in-distribution. But imagine we have here an out-of-distribution, and we want to say, okay, but it looks like it is not an out-of-distribution. Let's say StudX, for example. This is a real sample on the we made on the paper. Is that considering a test set on the first class of ImageNet, this is considered an in-distribution sample. And of course, those one are the nearest neighbor we have on the dataset. Looks like they are the same. We are right. And we consider actually the top one feature. We consistently see that somehow this first feature is focusing on the right thing. However, top 2 and top 3 features, while we separate by concept like these top 2 features, we have like all of those. We as humans also know that it's really strange that all of those have a man over there like holding the fish. And of course, the machine learning understood also too that this face actually is part of the important thing. So this is a biased feature that is biasing our model at the end. And here the same, the background is so consistent too on those samples. So somehow, this feature, it's okay for our artificial intelligence model. But these ones may be cancelled. I mean, do we really think that even if it's a really good a test, a really good model, which good accuracy, should consider the face or the background? Maybe we are biasing and we prefer it to delete it, because from a human point of view, we have that it is not ours, the purpose of our model. And also on a sample, I mean this. For this specific case, where we have an in-distribution case of a NINCO dataset, an out-of-distributed dataset, which are random images from the outside, is classified as a fox. And the nearest neighbors are actually those fox. And wherever we have this first top feature, we see that it's somehow predicted over there like on the corner of the sample, but on the if we visualize this specific feature on the other samples, we see that it actually makes sense for the Fox class. I mean, somehow the features detected for the out-of-distribution sample makes sense for the model because the features on the model learned for that, it's actually those make sense. However, even for the in-distribution, out-of-distribution case, we notice that the first one it's okay. The second one is predicting something about the stones of the fox. So even if it's an out-of-distribution sample, now we have a feature which is also biasing the model too, because a fox is not a fox because of the stones, but because of the fox. So here we have the second feature for the fox class is actually biasing our model. And also we could have like other features, like on the top 3 features, that the back of the fox, it actually hide it by the has been brown, but because of this part of the stones may look like in a human way, like the back of a fox. So it's actually the proposal we made for the pattern recognition, and I really didn't want to be so much mathematician about that. But I want to say about why I think XAI is a must. I think we proposed in the conclusions that XAI, from the point of view of on the high-risk proposal, is really important. So XAI on those cases are a must. Also, I think I didn't say before, is that XAI at the end must adapt to everything, to the data specific, to what we are applying, which algorithm we want to apply. And for example, as I developed a nearest neighbor hypothesis test, we need to show nearest neighbor proposal of explanation. So you also need to adapt to the own algorithm you're testing with. Also, we need to measure too the explanations. The explanation to say at the end which is more better or not, because if not, we are just showing graphical stuff. Like that's why the importance of the measuring. And well, different types of XAI are complementary. In which way? At the end, what we did on the pattern recognition, we are using heat maps, concept-based algorithms. The concept-based are actually local linear explanation. They are kind of agnostic. We are using nearest neighbor proposals, not in a prototypical way, but prototypes and counterfactuals may also be used with those stuff. And well, yeah, that would be the end of the talk. And here for your questions.
Doing great in terms of time, so he didn't have many questions during his PhD defense, but maybe we want to do that today, right? So, questions? I'm gonna let your mom first, then you. There you go, Victoria.
For congratulations for this job and this PhD, very nice PhD. And I have many questions, a couple of questions. First of all, when you was talking about the differential, you stop in the tangent line because you stop in the first differential. Yeah. What happens if you continue? Because the Taylor approach, as much as you consider the derivative, as much better is the approximation. So why you stop in the first one and not in the first one? Because it's less interpretable. I mean, at the end you are adding more features, more weights. I mean, the second, there are also proposals on explainability. Second derivative is not that difficult to understand, but why not third, why not fourth? At the end, we stop on the first one because of it's easier to understand at the end. The second one, there are proposals of integrated gradients with second derivatives and so on. So at the end, what they're talking is how acceleration makes for each direction of the explanation. So
the only thing is that why I consider that linear regression is better and why not another neural network, let's say. I mean, we are assuming at first that for the local linear explanation, we have G as a first, as a local linear application, which from my point of view is like the easiest way to afford the explanation. But of course, more complexity gives you less error, but more complex. So that's the main reason.
Another question is, all the mathematical background about explainability, you consider more or less on the literature? I will pose you all the question and then you answer. Okay. I think that you pass from analysis to statistic. So what is the state of the art in the future? What is next? Keeping all these things. So that's the questions.
What is next? From my point of view, the next thing, and that's why I started with this part, is the human in the loop. That's why when I first talk about red XAI and blue XAI, it's because the red proposal is changing changing the model, and the blue proposal is the model express itself. If we have the two ways, the go and back to the machine to the human, we have actually a human in the loop way. So we must focus on that. So that's why on this proposal, what I really wanted to do is to have a way of deleting several features, or maybe by changing my weight, by doubling it or something like that. From the human point of view, you enhance the model by this human knowledge. So again, the next step is making it easier to introduce the human knowledge, not just by reinforcement learning, because reinforcement learning make the model to maybe gaining more biases, learning more biases from their own reinforcement learning. So on this point, is more manually humankind, let's say.
In the approach of more statistic than analysis, or
in
the approach to go to the necessary?
To the human loop.
Yeah.
Maybe I am not.
Yes, the last part of the approach was statistic.
This one, you mean the
test hypothesis also?
Yeah. Okay, the test hypothesis,
yeah.
It's actually for the algorithm. It's not about the explainability section. So this specific part, is like we don't, on this point, we're not taking account into the explanations. Yeah. So the hypothesis is for considering that a specific sample is or it is not an out of distribution sample in terms of significance term. For the explanation part, it's just analysis. That's the.
Thank you very much.
We had a question first from the back, Alfonso.
I will shoot a bit of a weird question, but please tell me if it's too strange and then don't answer it. It's basically with explainability and those models that you're presenting, you're trying to kind of say what the model is taking into account from the data in order to take a decision on another. Is it possible to transfer these techniques that says where the model is putting attention into the quality of the data set itself? So the model is taking into account specific things because of the model itself, or also because of the quality of the data set? Is this transferable in order to measure how good is the data set?
Maybe a going word with Pedro? Just to help you out thinking.
What do you mean at the end? What we're measuring here, I mean, it's more about if we like the explanations a model gives us of data. I really need to figure it out. I'm not having an answer about that.
Because this pop out in that image that you were saying, the orange dots and then the blue dots, and you were kind of matching if it's from the same distribution. At the end there, they're talking about the data, right?
This one?
There, yeah, that's the data. So
the blue data and the orange one. But this is not about this is not about explainability. It's about the auto distribution problem, and it's about wherever you have the blue data at the end. If we have this data, from my point of view, I would not make an answer about the orange part. If I think that I have this orange auto distribution, this sample as an in distribution, and I have not considered it, maybe I should add it and say this is actually a data that I have not taken into account, but now that I saw that it's an auto distribution sample, this should be put into the training set, let's say. Now I think I got it.
It's kind of like a way of saying, okay, we are missing some data, some parts, right?
Yeah, but as we are talking now about open sets, R2 in this case, you may not have never a compact fulfilling our feature space. So somehow you will have empty spaces on this. So did I answer with that? Maybe, kind of.
Yeah. These are very open questions, though.
Yeah, for an open answer.
John, all yours.
So, what do you think? What is the relation between explainability and causality? Explainability and causality.
And causality?
Causality.
If I know Paco, it's actually forcing. Well, not forcing. I mean, let's say.
Yes, forcing. That's fine.
Making me study about that. The main thing is that explainability is actually about correlations. So considering we may have like this correlation for several features, and after this correlation, we may figure it out which points we should take into account, and after having a causal approximation. I think that would be more of a thing. And considering causality on explainability, like the talk we had with the tabular. Do we remember the professor who made the tabular approach, a causal approach about tables? Maybe we should make an explainability approach to check agnostically if the causal effects we are having are actually correlated, and those are the specific relation which we should focus to obtain the causal things. But explainability right now as I am taking it's just the correlation. This is not causality. So.
Cool. Wow, so many questions. Okay, let's start off here.
Not one is.
No, not that one. No?
About the algorithm in the first part, that when you have at the final of the model and the first step, you have the features of the image, or in the step one,
this one?
feature extraction is feature understandable in the image.
That's the main thing. There are several approaches. In this moment, we differentiate between the feature extractor and the classificator. Okay, so this one is usually the simplest one. Actually, MLP. So from here to here, we have the importance, and that's why we have the top end features and how we measure, and we have like really specific and really real answers about how much a certain feature is taken into account. But the visualization we have from here to there is more like LRP, like layer relevance propagation, like integrated gradients, or even Lime. We also may use from here to there like a Lime approximation. What does it mean? Is this specific feature over a whole data set? So what we have here is the feature structure, the features extracted by the feature structure. The top end features are actually made up here, and from here to there, to visualize each feature, we have this approximation from the agnostically or model dependent explanation or so on.
So you get the feature from the model, not
yeah.
the feature that you want to see.
Yeah. And it also correlates with the human in the loop way, because we are not assuming that this specific feature is actually something. So it's like whatever we have here, we discovered what is each of those features.
Nacho, please.
So first of all, thank you Iván for your talk. It was pretty interesting, although I know and I follow closely your related work. And yeah, I was wondering, because we've always talked about this model dependent and model agnostic explainable artificial intelligence. And I was recently reading about the mechanistic approach of developing transformers, and I want to know what are your thoughts on this way of tackling the architecture?
Stefan is not here. He's using actually sparse autoencoders, which is how the mechanistic approach. At first I was, at first I didn't like, but after checking, of course, in the literature that sparse autoencoders and checking, activating each of the sparse vectors attributes are making sparsity better on the feature space. This approach may be better with a sparse vector. So my thoughts about that is that I actually need to study that, and next approach would be this one. And talking about the sparsity, the sparse autoencoders, to figure it out. At first, we have here several data sets, but those ones are the same data set on ImageNet. And here we have a ResNet, which is the benchmark for the detection, the auto distribution detection, and vision transformers here. The visualizations we have here are the one we used in the paper. And vision transformer made up non-relevant, let's say, not useful visualization for detecting things. Probably if I use the sparse autoencoder things here, or attention rollout, or other specific vision transformer specific stuff, would be better. But on the ResNet, on CNNs, looks like it's not necessary, those sparsity, at least for the visualization. Did I?
Yeah. So I'm just curious that you said to Joel you are reading and you should read about causality. Are you planning to study this causality from the circuit approach that mechanistic transformers apply, or?
When I finish the build with the school, but yes, the answer is yes.
Alberto, you still want to go? Oh my God.
Oh my God. No, I'm looking good. Easy question. Okay, so from my point of view, XI is rather for auditioning, because you can understand whether the model is working properly, and also, according to Alfonso's question, it's just about the data, because somehow you can analyze, okay, why are these features taking something into account with the inference? They can be spurious or whatever. So for me, it's important. And talking about auditioning and the need to explain and to understand an output, when it comes to LLMs, this seems to be blurry. I mean, you get an answer, it's probabilistic answer because every word goes, with a flip of a coin, whatever. Can you transfer some of this knowledge to LLMs to trace the answer and to validate it, or at least to confront it? Or it's very complicated?
No, the main thing, there are several studies about instead of considering just input and output, taking into account the attention, and actually the algorithms that are actually considering this proposal about the attention layer-wise relevance is more about this not LLM but transformer way. Yeah, but attention it's also for vision transformers also. The main thing. Could you maybe could you repeat just a bit about the question? No.
The question is, can I use this theory to open the black box behind an LLM and to be able to, because this is not integrated, and I would like to have like debugger console for an LLM to say, okay, I have replied ibuprofen, but I could also say naxoprolol, whatever, no? When you need to think about a drug or whatever.
And
so
also,
is it possible to confront the output of an LLM using this kind of tracing mechanism?
With the algorithms or that Nacho is saying, yeah, with attention layer Y, which is specific with the attention layer, because another thing that what I was saying about the vision transformer that did not give relevant pictures is that when we have a transformer, the attention or the relevance is spread amongst the whole image, among the whole input. So it is not specific to specific features of the feature or words. Here it's actually for each of the words. The algorithms, you just need to check on attention layer-wise.
No, because it will also be wise to tell, for example, the user that the output comes from, because it pays a lot of attention on these words.
Yeah.
It highlights some of the words. Well, somehow it is like giving when it's reasoning, they provide. I'm searching for this because the user asked for this and that. This is the things I also like, because it guides me through the process that the LLM is doing through the inference, and this will make sense to me or not, or it's deviating for the prompt I give it to.
You're right. That's why I don't like the reasoning part. And actually, there are many papers that are saying that that you're even biasing the model by saying, no, you should take into account that, and you have the reasoning, and the reasoning looks like, but actually
it's tricky. It's very tricky. That's why I am,
attention layer-wise relevance, and also another thing that I really liked, and it also related with this. I actually at the end I like the image about this thing. If we have like a certain arrow about what we're doing with the model, somehow for each specific task, we may delete the whole model, the other part of the model, and make it cheaper by taking it small. Maybe we have a GPT-5 version that only works on artificial intelligence research on time series, and it's smaller as a GPT-2. Let's say. I mean, obviously, no. Or we don't care about emotional, and that's one thing that Paco Herrera said on one of his talks. That I don't want a decision maker GPT to think about emotional stuff. Let's say. I mean, we may delete all of those things that GPT-5 has.
Yeah.
So.
No, it's an interesting question. It's really open. Thanks for the answer. It was not
all right. You're not finished yet. So just because we are on a general purpose AI system school, and also because I feel like putting you on the spot, right? So I was wondering, what is your view on what is left to be done on explainable AI when it comes to general purpose AI systems? Is there any difference when you're talking about a model that is able to do more than one thing? or it could be useful for things like explaining emerging abilities, anything like that. How would you go about that? Please give me a solution and write a grant.
Is it out of distribution, maybe, somehow, a detector? I mean, just...
So you're saying we can use 2x for that?
No, it's the text. Well, maybe at a score, let's say, you're trained for several, you have GPAs that works on several stuff, on several tasks, and you know those tasks. And something else is coming on, is another task. And you detect it like, well, I don't know all these tasks, like this one, for example. And after figuring out that this task is a new one, you may consider as a human that there's an alert over there, like your model is having troubles or not about this specific sample. Is this a new task? And somehow you may have like a filled up.
No, but it's the other way around. Is that somehow the model actually is able to do something it was never programmed to do.
Yeah. Let's consider that you have this point over there.
Okay.
That you thought that your again it was in my mind. I trust me. You have these tasks over there, this new one. You can add this to the trainings, not training, but to the validation set, and now you have this task as one of the possible ones, and you may have the explanation over the ones that you are given to the model.
But how do I discover that something is really new, is emerging from a model? How do I explain that? Because I don't even know that the model is able to do the task. So unless I check it manually, how do you know that the model is doing something that?
So, but I mean, we have for new model, for this model, you want to check as we are in explainability. We want to audit about this specific task, this specific new one. You need to check it. If not,
yeah, that's the funny thing. You don't have anything to check against.
The check is the human. You have the alert, you have the possibility of checking. You don't even need to train if you want to add this specific task. Well, kind of. Well,
it's a difficult one.
It's really.
That's why I know I wasn't invited to his PhD viva just because of this.
Why not?
So
why not? It was not my thing.
Just one last question before we go for the break. So you said at the very end of your presentation, your conclusion, something like, well, explainability, XAI will need to adapt to everything in the problem. And therefore, for me, that feels like there is a need for automation. So, is it possible to learn to explain?
Yes.
So that we have a meta, some sort of meta-learning approach that we learn how to explain, and then you don't care about anything. You simply say, I need to explain whatever I think I need to explain.
Yeah.
Please tell me what I should be looking at. Shapley values.
At the end, at the end, where with each of the categorization, you may have this proposal with an if-else-if. You may have. You may choose between the Gradkamp potential, the Lime approximation, and
you need to predict which one is going to be best, right? So it's more like an AutoML, but an auto explainer.
Yeah, I like automation, but not that much. I mean, I really trust more in human instead of algorithm.
Oh well, I think that's going to be the end of the discussion for now. So 30-minute break. We've got a few posters there, so you can still do that if you want to. And then we come back for the final discussion. But just before we go, one more question. Nicely done. Muy bien. Welcome back. All right, shall we make a start? All right, for the final session of this winter school, what we decided to do is to put together, again, a discussion panel, and we took everybody who has been presented here, and they are still around, so they're going to be here with us. But in addition to them, we thought this wouldn't be a nice general purpose AI school without having something connected with us and trying to follow our conversations. I don't know if that is working or not, but it should be working. So we've got Gemini set up to speak to us. We've told Gemini that they are here, it's here with us, that I'm the person actually coordinating the discussion, and it should be quiet. We will see if it behaves or not, right? I have a few topics for today. I have more than 5. I doubt very much I will be able to speak about everything. But before I start with that, I thought the first thing I want to do is, if any one of you have any particular question for one of our speakers, I would like to start with that. So is there anything, any burning question, something that you've got there that you really wanted to ask to share? Or not you. Not you or Iván. Discussion with Iván was already quite intense, I think. He's still shaking a little bit. Well, is there anything you guys have? You're awfully quiet. Shall we ask ChatGPT, Gemini, if they got any question?
She doesn't know the topics yet.
She doesn't know the topics, but it hasn't been listening. Okay, Alfonso, please.
How much do you trust the security behind the chatbot that you're going to talk with now?
Can we ask it? Okay.
So one of the people of the audience said, is questioning about the safety of having you inside this discussion panel. So what's your opinion about it?
Oh, maybe
that's a valid concern. My participation is designed to provide diverse perspectives and information while operating within strict ethical and safety guidelines. I'm here to facilitate a constructive dialogue. Are there specific concerns you have regarding that?
Alfonso, do you have anything?
I do have concerns.
Yeah, go for it.
Yes, I do. It's
Go for it.
Who is putting the lines of that safety that the model says that it has?
The safety guidelines are typically determined by the developers and organizations responsible for the model, often based on ethical frameworks, industry standards, and regulatory requirements. These frameworks aim to prevent harm and ensure responsible use. Does that clarify things?
I would like to say that the developers may think about reinforcement learning for not doing so, but we're still not thinking about what you Gemini are actually thinking about. So.
All right.
I'm pausing the Gemini because otherwise, if she's actually listening, she's gonna try to reply to every single comment.
Well, it's been told not to do it, but who knows, right?
She cannot behave.
It's actually a really great way to start the conversation, because the first topic I wanted to bring to the room was something that Ramila actually asked me a couple of days ago, and she was wondering about how to do safeguarding in agentic AI systems. Was that more or less the question? Do you want to add in anything?
It's, my sense is from speaking with folks in the industry that 2026 is going to be, there will be a big focus and push with regards to AI agents and agentic workflows. And so what are the safeguards or the guardrails that's being researched right now? Because that's, I think, the biggest friction point for organizations.
So who here is working on agents? I think maybe that's the first question. One person. Any other person? 2 people. Anyone else? Only 2 people out of 50?
¿Y Nacho Antequera no está?
Ah, he left.
Okay. Okay.
That'll be recorded now on YouTube. He's not here.
I think that the main research that's going to be done about agentic AI, or at least where I think we should focus is about making really smaller language model to make it able to make just specific tasks. Not making a general purpose AI, but maybe focusing on the what they say in the literature, orchestra stuff. Like there's one LLM, one agent that knows which agents it has, or to train a little agents, and throwing the agents on that way, but making it like smaller, so they can be auditable at the end. So from a point of view, it should be, and also that's another stuff, like those smaller agents. If you have, let's say, a GPT-5 model working as an agent, and you have another GPT-5 agent working to choose different things, you have two really big models working on really small tasks. So somehow when you make them smaller, you democratize them, make a smaller business to have the access of these technologies. And you also audit, you have the possibility of audition on those stuff.
But you don't prevent the problem, right? Because still the whole system is just a difference between going for a single model or multiple models, all of them connected. But at the end of the day, they all work as one thing, and we need to put something to control that all of those smaller entities do not end up doing something that they shouldn't be doing, right? So I think it's a really valid concern. But sure.
Yeah, maybe I'm not researching agentic AI, but here's a cynical comment. Like, in a certain sense, even if we research and are able to make sure that certain LLMs act ethically, we have to make sure that there's incentives for businesses to behave unethically. So I would say that the most important part is that we properly inform our members of parliament, like how they should make the rules such that AIs and businesses are forced to act ethically.
Yeah. If they don't know how to rule, I mean,
in members of parliament, they have to get advice somehow. So,
Pedro.
Okay, I can add something to the discussion. First, typically when we are talking about agent AI, we are talking about distributed environments, right? And in distributed environments, you can use federated learning. That one of the main advantages of using federated learning is to somehow guarantee privacy inside the data. This is the first question. The other question is, in terms of, for instance, oversampling techniques, if you do a research on that area, you will see that the evolution of that techniques is in fact regarding to privacy and fairness. So now oversampling typically likes to know about anonymity things related to data. So the goal is not only to create synthetic data anymore, is to create synthetic data that guarantee privacy and also sometimes that guarantee fairness of the data itself. So I think this is a natural evolution, and privacy will be a hot topic for many, many years.
Juan, you have a question.
Well, answering Ramira's questions, right now in the agentic workflow environment, there are two schools, for say in a way. In one hand, we have the type of implementation when we implement the agent or multiple agents as a graph, so we know exactly what they are going to do. And the only thing the LLM is going to do is answer questioning, answer question or do a basic search, so there is no problem with that. The only thing that it could go wrong is if the workflow implemented by the developer is wrong. So in that way, we are not concerned with the problem about going rogue or doing malicious thing, because in that kind of evaluation implementation, there is not that problem, because everything is at the power of the developer. But there is a problem with that is because with that kind of implementation, it shows that the performance is lower than letting organize themselves, the agents, for example, having an orchestrator and planning all the action that they are going to do and reducing the human intervention in the most possible. So with that perspective, the agents are working alone and they're working in teams or grouping or just implementing basic strategies, but they are not under human supervision. And with the problem with that is that the only mechanism we have to prevent the agents to do bad things or to make or to put safe rails is to let them put them. It is to have a consensus big enough and let them discuss it big enough to understand what are the things that they can do and they cannot do. So in one hand we have a very good performance but no control over the process, and in the other hand we have the workflows that they have to do. They have to be done by hand, but we have totally control about what the things they can do or the guardrails they can do or will do.
Could we not have just an ethical agent that will be supervising the whole thing?
It's a validator. Could be a validator.
So it's like a supervisor there just checking that what the individual agents are doing might not amount to much, actually not unethical, but if you start adding up, maybe end up being a problem. So there should be that orchestrator we're talking about, maybe should be also using some sort of ethical AI agent.
I mean, I just wonder if that will certainly solve for that issue where an agent does things that you haven't asked it for. I've experienced that. I built a web app and then the next day I go back to the program and I see that it's deleted certain sections of it. And I didn't ask for that. So if we have something else, another agent monitoring a group of agents that are just performing a series of smaller tasks.
This reminds me of a paper that on synthetic workflow and artificial intelligence, an LLM, it was trained to answer, well, not even trained, LLM, to answer mails and so on, and to make a fake enterprise mailing process. Like, okay, the thing is that on the experiment, on a certain point, the mails gave the model, like, let's say, like the president of the company was thinking about to shut down the artificial intelligence, because somehow it's better to change to another one, or so they shut down. And the artificial intelligence, like in 90% of cases, or it depends on if it's cloud or GPT or so on, blackmail the president with certain stuff, like we know because they put the give them another mail where someone says that the president has an affair with someone, so blackmailing. So this is more or less like the concern you would have, like an artificial intelligence which knows how to send mails, try not to blackmail people. That would be explaining those stuff and checking on the internal architecture which vector of the features are about the malignant thing is, from my point of view, the explainability guide, that you should delete this bias and check it with a human way, more than, well, my point of view about this kind of debiasing is more human-centered than automatically centered, like making everything automatic. So I would focus to more explanation, more transparent, more interpretability, and debiasing methods to human in the loop to make everything auditable.
Please go.
Because I agree with him, because if you put an agency supervising the other agents, will it be create
a secret messages?
It will create a good pressure, so the agency will try to trick the supervisor.
Yeah,
it could be.
This is kind of a thing that it could be happening in a GAN style thing too. So yes.
I'm not fully sure if Ramila was worried about mostly what we call emergent abilities, so that not that the agent has misalignment with the task that we are actually asking them to do, but discovering that the agent is already trained to solve something we didn't know beforehand. So I don't know if this is part of your concern.
Sure.
I'm not fully sure this is actually a problem you can actually solve. Because there are two ways of doing this. Either you are completely sure that the agent does not do anything outside of the box, and therefore you get the wings of this model, and or you let them have these abilities, create bigger models, that is the actual pathway, for example, for ChatGPT or these bigger LLMs, and have better quality, better results, but also uncontrollable experience in some cases. So I think that would depend on the scenario you are applying this type of techniques. If it is really useful to have them cut down in a short box of options, then I will choose all the safety tools that I can apply to it. Otherwise, I'm not fully sure.
Like a kill switch.
Yes, absolutely. The red button of Google, no? Like, should I ask?
Yeah, I think the problem is we haven't been feeding everything we said.
Yeah.
It's going to be a little bit challenging to tell it to go to YouTube and watch the whole video. But maybe you can try to summarize a bit what our point is. But José wants to...
I would like to add something in the direction that Pedro was mentioning about the federated learning. This is something that has been used also for optimization a lot. I mean, in the sense that if you want to be sure that there is no fake agent that is trying to give you a different answer of what is really the optimum of the thing. I mean, I'm just thinking optimization, but you can think about the loss function of something that you want to learn. It's the same. So then typically you will have several people which are supposedly cooperating, in which they are sharing their result but not their data. Yeah. And then what they have trained. So in doing so and having an average, somehow there are methods of detecting the ones that are outliers. So that's one of the ways in which people are doing. So I mean, I just want to reinforce that idea of federated learning, which is in that direction.
Yes, the idea behind federated is not only the distribution part, but not share the data.
Not share the data.
Share the training model.
You share just the result of your training model, but you don't share the data. And then in that way, you're not giving away for free anything that you are developing in your company or in whatever your research center. At the same time, you are supposedly cooperating with others, but maybe you can identify the wrong people. Yes.
Any other question in the room before we try to ask Gemini what they think?
I would like to point out a little thing about this federated learning scheme that is very interesting as well. But I've also read a little bit about this because I'm still worried about that the model is doing something that we actually don't know. And there is this kind of attacks in federated learning that are called backdoor attacks, I think. I always miss, there are Byzantine and backdoor attacks. And I think that the backdoor attack, what tries is to...
Has a target. Yeah, Byzantine is destroying everything.
Yeah, I think that the backdoor what does is trying to make the model learn a task it was not actually intended to learn. And so even we are preserving the safety of the data, we are not preserving the safety of the model in this case. So that could be also one option. Should I?
Speak to it and see what it says.
We have been discussing on agentic AI and safeguarding, and we've been talking about federated learning as a case of data privacy, and also about several techniques and other stuff about the model safety. What are your concerns and opinion on agentic AI and safeguarding?
Keep it short. All right, let's see. Oh, it's your turn. Come on. Don't be shy. You're worse than my students. Nope.
The servers are down.
Yeah. She's tired.
Oh.
It already failed.
You didn't pay enough.
Probably we didn't. You didn't recharge. You can top up your...
if you'd like to.
All right, so let's move on to the next topic. I have a few of them, but I'm going to stop by one of them, actually, that you told me to introduce, that is fragmentation of LLMs. So nowadays, it's difficult to choose. So how do a user know what to choose? Local LLM, small LLM, a large LLM, OpenAI? What do we use? Thoughts?
I can add additional noise.
Additional noise to the distribution of my question. Okay, let's go for it.
The additional noise is that how can you choose the LLM version of it, and at the end, how you compare different LLMs from different companies that are open source. I mean, imagine this scenario. Imagine that I have a problem that I am using an LLM to solve. But of course, as an academic guy, I'm using an open source LLM, a free one. So how can I say at the end that this LLM doesn't work? I mean, I'm using a free version of it. So, you understand me? So at the end, my conclusions could be this LLM doesn't work for my scenario, but I'm using a free version of it. And finally, how we can compare different LLMs. I mean, we are using typically free versions of it, and we are saying that this version of the LLM is better than the other version, and are better the LLM from another company. But at the end, I don't know if we are comparing the same thing.
I'm liking this very much, because probably you thought, guys, that we were going to answer every question. But actually, right now, he fired at you guys. So, anyone in the room? Tim, please.
I mean, for my work, I do a lot of LLM stuff and agent stuff. We just have internal benchmarks, so we just run it the same as do for anything else. It's just a different model. If you don't have access to all the models, it's the same as if you didn't run all the benchmarks. So for this use case, for this model, it works or not.
How big is that benchmark? Can you say?
Not as big as we want it to be, but it seems to work well for our use case. But that's it. Just invest in benchmarking your problems.
There are also some ILO pages or somehow.
Yeah, I mean, there's the stuff if you want to put the more general stuff, but if you've got task-specific use cases, then
the same.
Yeah, I don't think it's anything different when you have machine learning models and that in this case.
Yeah,
you do what we always do.
Yeah,
sorry, I don't think it's comparable. I believe. It doesn't. No, it is not. It is not. It is not. Because when you are using a classical approach of machine learning, you are using the full version of it. You are using a transformer, a full version of transformers, and etc.
Sure.
When you are using a free version of LLM, you are not using the full version.
Yeah, but
so at the end, let me finish. Imagine this: you are using a free version of a specific LLM that there is only that version in the market. So and afterwards, you are using a free version of an LLM that exists a paid version of in the market. So, from my perspective, you cannot compare both.
So you can compare them because you either pay, or if you don't want to pay.
You cannot compare because you are comparing different things. You are comparing a version that is half of half of the requirements, and you are comparing another version that is fully complete version of the LLM.
But I think you're trying to answer a different question, because the question is just which LLM or which model.
No, I don't care about that question at all. No. But I want to understand if the comparison is fair.
Oh, it's fair?
Yes, it's fair. This is my point. It's fair in terms of the version of the LLM that you are using. So imagine, when you have an LLM, you train the LLM with a lot of data. Imagine that I put a free version to the market that only train half of that volume of data. So when I put in the market for free, and I have the other one that is paid, okay? And after that, you want to compare another version of another LLM that is free because the company thinks it is better to put free because it's a small company, etc. My question is, you can compare these two LLMs, the one that is free by a company that cut in half the volume of data that trained the free version, and you compare the free version of another company that do whatever they can to put that LLM in the market. My question is that, is fair this comparison, yes or no?
Yeah.
I think not. No, it is not. It is not.
I think it all depends. I think he's got a much more industry
of course,
vision of it, and you are the academic who wants to have specifically all the hyperparameters under control.
I think at the end you cannot conclude nothing.
Well, but the conclusion is more just which models can develop from a use case, which
Yeah.
is perfectly valid. Anything else is kind of irrelevant.
Yeah, it is your opinion, not mine. Juan, please, go ahead.
I think that the perspective of this problem is wrong, because you should be agnostic of the model. If you are truly doing a good software engineering, if you are doing truly a good job, it doesn't matter which model are you using, because it is a matter of performance and preference. It is nothing more. It is not, and it depends on the user, it depends on the company, it depends on everything. But it's for every job there will be one best model, and it is absurd to say because it is open source. No, it is. I agree with Timothy in that way that it is for your problem, which are the ones that check more of your requisites or needs, because that is the point. Because if you are doing truly a good software engineer, or if you are doing computer science, if you are doing really a good job, it doesn't matter which model are you using, because the important thing is what is behind, what is under, what is your part of the infrastructure. Because a small company will not have the infrastructure, will not have the servers to host a big model, and they will have to use proprietary model. So if you are a small company, you don't have anything to choice, you don't have anything to say or choice, because you don't have the power to do it. And the problem is, if you are centering the discussion in which model using, I think you are not getting the full picture, but because that is not the point. In order to survive in this agentic era, it is not to focus only in the model, but all the things that come with it. How we give, what is the innovation that you are apporting, or what is the innovation that you are truly saying in your paper, more than which is the best model, because that will, in a year, will be obsolete, because there will be a new open source model.
Yeah, that's a really good point. I think another thing that we could also look at within this is for the benchmarking. Sometimes it's not that easy to measure how well it performed, right? Because sometimes you end up using an LLM to measure how good that was. Because when we are talking about something a little bit more subjective, so like, oh, is that introduction well written? Maybe for me it is, because I understood it, so I found it nice and easy, but maybe Jacob reads it and says, that's bullshit. Because clearly some Spanish person wrote it. So that's a little bit of an issue as well, right? How do we handle that? How are you guys gonna solve that in the future? And I make the money in the meantime.
Actually, that's why I think agentic AI it's quite better, because whenever your task is really more specified, not writing an introduction and so on, but that you actually may develop really real benchmarks, like taking into account like how long would be your answer, if your program, because I'm talking about an agent that program, passed those tests or make enough tests or not more tests. On this way, you may measure those specific tasks you're doing. If you're having a general AI without those specific benchmark, as you have a task, you have your preferences, and with your preferences, you may develop several measures. If you're not having those, you're training things in internet as first GPTs, which needed.
But it's a little bit like explainability sometimes. How do you measure how good is an explanation? So how do you measure how good is something that is not something you can quantify easily, let's say? You're going to look for some features in that answer, for example, which is important, obviously, but and how quickly, blah, blah.
Yeah.
But still there is a matter of what you like
Subjectivity.
the most, right? Yeah.
So as the question poser, I want to give my insights about this, and I'm not fully sure I totally agree that the comparison is not fair for me either. And someone said yesterday in the discussion panel that we tend to repeat in this LLM and AI era, we tend to repeat again and again experimental frameworks and conclusions. And I feel the same when regarding the LLMs. I feel that there is actually very little difference to using one on another on a basic user. And what I'm seeing is that every single company, time that it arrives to, or it has 50 or 100 employees, they want actually to have their own LLM, and they will keep it doing over and over again. And we will end up having small LLMs for tourism, for every single city we visit, LLMs for every single small task that I actually come around my house. And I think this is not scalable and is not aligned with what we were talking about 2 years before, 3 years before, which was green AI. We were really worried about consuming and servers. Even, for example, NVIDIA put it ARM processors on their servers because we were really worried about power consumption. We are not anymore, or I don't believe so. So I'm worried about this explosion and fragmentation of LLMs combined with this green AI era that we were having till yesterday.
I think we already had this discussion last time. We were also talking about agentic AI and so on. And maybe for everyone in the audience, a question: should every company, not persons actually, be allowed to, as they can, use all their potential to produce or consume energy and water and so on, without any, like, as much as they can, as they pay? They know they have the money, they can make all the prediction with their LLMs, with the ChatGPT 7, and as they can, and they have the infrastructure. And should they really be allowed to use all of this energy?
How interesting. And actually this question actually aligns kind of well with one of them that was asked, and the person decided to remain anonymous. I'm gonna call him the party planner, so you know who he is. Okay. So he was telling me that he believes that companies like ChatGPT or Gemini will stop giving us this service.
Of course.
Eventually, because it's
of course
going up. So I would like to hear your opinions. I can already hear this. Of course, that's definitely happening.
Of course.
So what are we gonna do? What is the business model that will be making OpenAI and other companies make money without destroying the world? Please, go ahead.
First of all, they create the need.
Yeah, the need, they created it already. I mean,
and then
how are we gonna finish?
They can whatever they want. They decide whatever they want, because if you have a need, or if you have a daily need to use ChatGPT.
But if they don't have the resources, if there is no water,
I think those companies will have also whatever they need.
Sure.
I feel like this is more or less the standard how now big companies operate, in the sense that you invest a lot of money, then as Pedro said, you create a need, and then once everybody is getting used to it, then the competition starts, and then you raise prices. And for AI models, that doesn't have to mean that it's like you have to pay a monetary price, but it could also be that advertisement is going to be introduced, either subtly in the sense of you just get a pop-up, or very subtly in the sense that it suddenly, if you ask for a recommendation to go somewhere, that the one that paid the most will be that restaurant will get recommended or something. So I'm inclined to think that it will either go, it's most likely to go in this advert direction, and then you can have pay big bucks for having less of that. But
I'm hoping they don't put the advertising when I tell them to write my emails, right? Because if they put it in the middle of everything,
have you seen Black Mirror episode focusing actually on this kind of stuff? Like, well, it's about a person who's been dead, mentally dead, and they develop an artificial intelligence or a part of the brain which substitutes this part of the brain. So now the women can live again and also have like several improvement of their mind. The thing is that you add advertisement to this stuff. You add several. You have to pay to feel more, like feeling stuff, because you have something in your brain. So if you have focusing again in ChatGPT, wherever we have this kind of ChatGPT paid and also with advertisement, and so with the need of using ChatGPT, we are actually like in the hand of companies. So my point of view is that we should shut down several stuff on the other like enterprises in general.
I think that, as many people said, when something is free, the price is due. So I think that our data are the petroleum of the century 21, and we are bringing them to who knows. And of course, I think that the government, at least, no, I am not talking about local government, but for instance, Europe or something like this, have to take care of this, because we have to be sure to whom we bring our data, because this changes even the democracy of the world. So we have to be sure what we do with our data. If something is free, the price is due.
Alfonso, please.
In my previous work experience, my mentor went to Silicon Valley, to Microsoft, to give a speech about how the eco and green corporate life is going right now, and the way of work of companies such as Amazon or Microsoft actually is they have like a steep pen. You cannot consume more than X, or in case that you do, what you do is paying some companies money that plant some trees or that do some carbon specific task in order to reduce their the footprint. And I believe that this is a measure, but also a very dark measure. So you are able to do whatever you want with the carbon footprint, and if you pay enough to clean your image. So that's a very weird way to do it, but it's the way that works right now in that huge companies.
How interesting. Ramila?
Yeah, I mean, that is a good point. I agree. It doesn't really negate the negative impact that they're making, but with regards to the cost of the inputs and the resources going into building these models, I do think that there is a first mover advantage. I don't know if that is going to be OpenAI in the end, but that's why you have companies like Google and Amazon investing so much or ramping up their investments for 2026, because they know this is how to have a sort of winner-takes-all approach, and you basically can exclude the other players from the market. And the cost of the inputs into these models is just going to make it difficult for the less resourced and smaller players or new entrants into the space. So that's why they're really being very aggressive for this year.
That is incredible, because I feel that we've connected the question before and this one.
Yeah, the two together. Yeah.
Because now I was wondering about this fragmentation that we posed early, and now it seems that maybe there's something related with this in terms of geopolitical positioning of having each of the models, and having the ability of having one of these, not state of the art, but maybe an open source and an LLM available for us, even though Anthropic or Gemini or whatever is shut down for us. Or, yeah, if it costs, for example, 200 euros a month.
In the end, the costs get passed on to the consumer. The shareholders make profits, and enterprises that are well-resourced will leverage the technology to come up with their own in-house solutions. But in the end, the consumer gets hurt, and competition.
Tim?
Well, that's all predicated on the assumption that the amount of compute and the development of these AI systems is requiring more and more growth. If eventually it plateaus or stops and compute keeps on growing, how the amount of access, or the ease of access to these models will start to become much easier for people to have access to these people. We have phones now, access to 20 years ago. And it could be that this first mover advantage actually backfires because they're going to start carrying all this debt and weight of the heavy investment. If you look at something like the early CDNs like funds versus Cloudflare today, where Cloudflare is actually comparable, not bigger, because they weren't the first to be there. And so it could be something like that we see in 10 years' time. Access to the models is just ubiquitous and everyone just has it because we solved some part of the random computing. It just makes it trivial.
Very interesting, right? We all have an opinion on what might happen. What I thought it was going to happen, it's not like it will be just one single LLM. I thought it was going to be more like you have Netflix, but then you also have to pay for ACM, and if you have to pay for another thing, so they would probably specialize on things that you say, oh yeah, but if you want to do this kind of job, you need to pay for the Google one, or the OpenAI one, or actually, yes, your own thing. And so I thought that was going to be the case, not like, and they will have like a piece of the cake for each one of them, and they would normally fight a little bit, but they get kind of comfortable, right? So if you look at Netflix and Amazon, they don't fight as much. They do the same thing, they just simply sell different stuff, right?
They'll compete, but almost like compete.
But they, in a healthy way, right?
Collaborate.
Yeah. Any other thing in the room?
I don't know, but me as a user, I prefer to use a model that is more aligned with my values. For example, I prefer to use Claude instead of ChatGPT because I know that they do investigation about the explainability of their models. They have a lot of investigation about how can the model be more safer for the user. So I don't know if the other way to see it is to use a different model is more aligned with your values, like for example, or sustainability or something like that.
Yeah, definitely a great point, right? So we will all use whatever you also think is the best for and closer to your values, right? So
Yeah.
yeah, it's fantastic. Cool. I think I want to stop a little bit with the LLM because I think we could be talking about LLMs the whole day and more. And also because we have a couple of mathematicians in the room, I wanted to go and change a little bit the topic. And the topic was math and AI. And the question I have for you guys is, how do I do to understand you? What do I need to do? And then maybe you ask. Yeah. So how do we catch up with each other, language, let's say, and terminology to be able to understand each other? Because I think at the end of the day, we are actually speaking about the same thing. It's just simply the communication becomes a little bit difficult because you put a lot of formulas in there, and it's like, oh, what? And maybe you see a lot of code, and you're like, nah, right? So yeah. Nacho, please put the microphone away.
Well, I think this is a task that is in general for mathematical modeling. You can talk about the value of mathematical modeling in any other area, like in biology or in physics, and this is just a matter of when you discuss about the same thing at the end of the day, you just by discussing and collaborating in something, you end up with a common language, and then you understand each other and what the objectives are. Typically, what I find is that the goals are a little bit different in a sense. The mathematicians will think, I want to solve this particular problem, I want to solve whatever, global optimization or whatever. You have something that is your goal, while somehow you are much more grounded to earth in the sense of saying, okay, I want just how to do this in this particular problem, to solve this for that particular purpose. But I think there are a lot of things that we can learn from each other. And just talking about the specific things, for instance, we talk about things that we are both interested in. So anything related to optimization, inverse problems, data simulation, or how to properly compare data sets. I mean, I'm not doing that, but there are mathematicians that do different techniques for doing all of this. So I think, like in many other different areas, you know, there is a fuzzy region between the two, and then that precisely having places in which that talk or that discussion goes on is important, and this is just a matter of time, I would say. Time and will to that you can see that some of the ideas that you have from the other side might help you. And I see directions in both sides. One could say, okay, I can use machine learning techniques to solve, I don't know, a particular PDE. I want to approximate, I mean, I want to have uncertainty quantification on the parameters of a damper. I know what the equation is. I don't care too much about, particularly as a mathematician, to find what are the optimal values of those parameters that can be used for the purpose, but I will need a numerical method to solve that. So, you know, that's one direction, but the other direction is, can some of the, well, I mean, developments in mathematics can help to improve the algorithms. So both sides are interesting, and I think in both sides there are plenty of things to do and to explore.
If I have to answer this question, I think in the history, because I think that the 20th century is in the basement that we don't understand each other, and I will explain you why. Classic physics works, but derivation that is essential in classic physics is a limit, and the notion of the limit is the Napoleon, is this time. So the science was developed without no rigor, because the limit was, and what is a real number? We are talking about Hilbert and the beginning of the last century. So at the beginning of the last century, the rigor, the tool for the rigor was there. In 20 years later, with classes, with quantum physics and so on, the Banach spaces, the Hilbert spaces was developed by people who was a mix, because John von Neumann is a physician, is a mathematician. How these people were people very clever, very polyvalent. And after that, when mathematicians have rigor, at least we have rigor, at least we can understand, at least we have finite dimension, then they became like autistic. So they was working by themselves, and also physics, until the point that for my mathematician it's very difficult to read a book of physics, and vice versa, because they use Dirac language and we use another language, so there are really problems. And then we were divorced, totally divorced. And then in this century 21, computer science emerged, and we are divorced. Mathematicians are divorced for physicians, and then computer science arises like a new science. So we have to go back again to be together. We have to create the culture to be together, the culture to talk each other, the culture to be interdisciplinary. Because of this, I applaud this initiative. So this is good. So I know that talk of mathematics probably are very boring for everybody, but I think that we have to be used to be together, and to try to understand, to try to collaborate as much as possible. We have to do this effort, but we don't have a tradition, recent tradition on this.
Do you think hybrid people, I'm gonna call them hybrid, like the three of them, that they do have a background in both math and computer science, they have an advantage? Because they understand both worlds to understand? Or you at the end, it's like speaking multiple language, that at the end of the day you speak more one language than the other? Is it that way? How does it feel for you, for example?
Of course that helps. But not necessarily, no, it's not the only thing. I mean, it helps you to make better the bridge between the two worlds. That's certainly true. And sometimes you can make it, and you can help other people to connect due to that. But I think is in some sense what Maria Victoria was saying is true. In some part of the 20th century, there was this division between the different areas, which they, for whatever reasons, either not scientifically, most of them, they wanted to make them separate, and that has been a big mistake, and we can see that all in science. For the development of science, there are really no boundaries. So the best and where the places normally work is that you just try to find what's the common goal, what's the discussion, what's the problem, what you can contribute to that particular problem, and then immediately you start to finding the common language, as you were saying, that you can communicate and advance. So, and then everything is like, you roll in some direction and then take a particular problem, like what the mathematicians like to do is you focus on a particular problem, a little piece of the whole thing, and try to get it done or understand that particular problem as deep as you can. So that is a bit the different perspective, I would say. But I think there is a lot of potential now in that interplay between computer science and mathematics. So,
can we really use LLMs to help with that, you guys, in your experience?
Well, people have been using anyhow ChatGPT. There are the famous mathematicians are using now ChatGPT to prove theorems, particularly in algebra or in number theory. So like Terence Tao in UCLA or Kevin Vassar at Imperial College, they have published a paper like not long ago in which they prove certain conjectures of number theory by using ChatGPT to have them in the proof, and then they send the proof on a validation software that is called Links to check that the proof is fully correct. So there are people that are trying to go in that direction, of course, in math too. For the time being, most of the results that have been obtained by using that approach are related to what I would say algebra and number theory somehow because they have a set of axioms that are much smaller, and then they can rely on that. But you never know how far this can go later. So less in analytic directions, or much less in numerical schemes directions, but in those directions.
Thank you very much. Any other question in the room? Alberto, please.
As Maria Victoria was pointing out, physics were advancing before all the formalization made by Hilbert and all these people in the beginning of the 20th century. So we were having advances in physics without this mathematical machinery. Right now, I think computer science is in a kind of a similar stage as in quantum mechanics happened. But I think that probably the advances that we have achieved in computer science are way bigger than they were happening in physics, maybe. So, do you think is it going to be possible to have a formal model that could arrange everything that has been happening in deep learning and in artificial intelligence for the past 20 years, which is a lot?
That it's possible to advance in knowledge without a solid math foundation. This is what I said. Yes, unfortunately, I think that things are not together. Of course, that in physics the difference was 200 years, and now in mathematical computer science the fast will be not so great. But I think that first our application first is to survive, and then mathematicians like put order in the theory. But if you don't have the two phases, I think that the science be flat. So it's a process, but it's like the sine and the cosine have to be together, but they are not in the same phase. But one is after the other. I think that this is necessarily, but probably that develop be at the same time. Probably not. And for me, it would not be a surprise. And concerning something that we were talking before about hybrid people, well, now we have double degrees, but we don't have hybrid people, in my opinion. So the double degrees are because they create a common space just to organize an academic organization to be compatible to finish two things in a period of time. But these are not hybrid people because the teachers are not hybrid. So who will be hybrid people? Probably your students, if you like. But it's not my generation, it's your generation. So this,
next generation.
Yes, it's the next generation. Yes. So depend on you.
You're making me feel very old now. But yes,
depend on you. And probably with these hybrid people, things will be at the same time, simultaneously. But right now, I don't expect so. but have to be close each other some way.
So maybe we connect people, mathematicians, AI, and computer scientists all in one brain, right? Like that.
Physics,
And physics, yeah. Why not? Yeah, why not?
I believe it's not about the degree that you have already. I believe it's about people who are willing to cross the border between knowledge areas. So it's not about having, for example, I'm a mathematician and a computer scientist, but that does not matter, because what you are saying about hybrid people is people willing to cross this border in one direction and another way. So those are the ones that connect the bridges that make us possible, for example, to use the kernel properties to actually come down to a sparsification technique to make a kernel or an attention mechanism much more efficient. If this bridge wouldn't have existed, this approximation wouldn't have any base. So I think those people are the core of the advancement of research.
Only to add one thing. Now we have a concept that is already emerged, and the concept is world model. I don't know if you already heard. World model. What it means? It means that you will have at the same environment the simulation, the data mining approach, the validation of the results, everything together. So the concept is world model, and to reach that we need multidisciplinary persons, and probably persons that dominate more than one domain. So check world model. Okay?
That's a great addition. I think the terminology is changing towards that right now, that I say it like a bigger digital twin, but it's the same thing at the end of the day. Is there any other question in the room? If not, we are already at the end of this session, so I want to thank you all once again for coming all the way to Granada. I hope you enjoyed the winter school. I did, and I'm gonna repeat if I can next year, but if not, I hope you really enjoyed it. We will share all the materials we had from the speakers as soon as possible, and I hope to see you around. Thank you.
You have to say about the
certificate. Yeah, the certificate will be sent to you by email tomorrow. Okay.